Communication Networks. This is session 1A in the theme Intelligent Systems. So thank you very much. Please take your seats. And I give a warm welcome to our session chair, Professor Ajit Kumar Chaturvedi, who is the Vice Chancellor of Banaras Hindu University, Varanasi, and also a professor in the Electrical Engineering Department at IIT Kanpur. Professor Ajit Chaturvedi had joined the Banaras Hindu University as a lecturer in the Department of Electronics Engineering in the Institute of Technology, now IIT BHU in 1994. Subsequently, he served the Department of Electronics and Computer Engineering at IIT Roorkee before moving to IIT Kanpur in 1999, where he held multiple leadership roles, including Head of the Department of Electrical Engineering, Dean of Research and Development, and Deputy Director. Professor Chaturvedi took charge as Director of IIT Roorkee in January 2017, a position he held until October 2022. During this period, he also served as Director of IIAS Shimla and Director of IIT Mandi from July 2020 to January 2022. On July 31st, 2025, he was appointed as the 29th Vice Chancellor of Banaras Hindu University. Professor Chaturvedi earned his BTech, MTech and PhD in Electrical Engineering from IIT Kanpur. He was the coordinator of the BSNL IIT Telecom Center of Excellence, which has undertaken numerous projects for the Indian telecom sector. In recognition of his outstanding contributions to teaching and research, Professor Chaturvedi has received several recognitions, including the INSA Teachers Award, the Distinguished Teacher Award of IIT Kanpur, and the Tangent to One Fellowship from Nanyang Technological University, Singapore. In 2024, IIT Kanpur confirmed him the Institute Fellowship. He is a founding member of the Telecom Standards Development Society of India. Professor Chaturvedi was a member of the Government of India's Department of Telecom Committee that recommended criteria for spectrum allocation to telecom operators in 2008. Professor Chaturvedi's research interests include communication theory and wireless communications. He has worked on several problems in the domain of the physical layer, such as waveform shaping, sequence design, MIMO systems, etc. With that, I welcome Professor Chaturvedi as the chair of this session on next generation communication networks. Thank you.
Welcome to this session after the very interesting plenary talk, the session on next generation communication networks. And we have three very distinguished speakers talking about three very relevant topics in three different directions. So I'm sure we are going to get a very exciting session.
Good morning. Yeah, okay. Yeah. So first of all, I'm privileged to be here and share the experiences. And thank you to IIT Kanpur and INAE for inviting. And we'll start. Yeah. So topic of my talk is next generation network and key practical directions. So when we say key practical directions, we are talking about future. Now future can be 2-year, 5-year, 10-year, it could be 20-year, right? But what is that of important need for all of us? And we are in critical junction right now. 5G has come to deployment and 6G is about to come. So keeping all that in mind, we will keep a focus on what is for immediate next 5 years. So when I say future, my focus will be immediate next 5 to 10 years. Of course, many of you are working in great areas. Possibly they will come little bit more than that. So please don't feel bad that, okay, some technology is still not covered by you. That is just because, focus is more towards practical aspects towards the next 4 or 5 years. Yeah. Okay. With that, I'll start. So what is 6G? 6G is basically, as you can see here, and we have seen this example since morning, right? A surgeon wanting to do operation anywhere, he could be anywhere, the patient could be anywhere, and glasses are, XR, right? They can have all the parameters, right? It's a very simplistic diagram. That is all what we understand, and we know the history, how 2G came, 3G came, 4G came, 5G came. Approximately every G incremented data rate, parameters like latency by 10x, right? So is 6G so simple that we just improve what 5G offer and that is called 6G? So that's where a lot of thinking is happening right now in both industry and academia, that should we just make it 10 times more better and just call it 6G, or there is something more to it, right? So that's where we are coming into this aspect, and we are discovering a lot of challenges. What are those challenges? Those challenges are that while you achieve this KPI parameter, right, how can we achieve all that by keeping cost in mind, right? How can we do all that by keeping energy efficiency in mind, right? How can we do, when we are planning to deploy it, take care of diverse requirements, both from application side as well as the, where it gets deployed, yeah? Using satellite, using, mobile and terrestrial network and so on. And also having a AI native thinking. In 5G also AI is introduced, but most of the things in 5G are afterthought. They were not there in the beginning and later they got introduced. So not very well integrated. So how can we do practically everything from the start? So why do we need 6G, right? So of course these are certain very important applications. Probably 5G was a little bit ahead of time, applications were not there, right? Now, as we saw, last year, one phone company launched XR. Last week, Samsung itself launched XR, right? So these devices are now coming to practical commercial domain, right? They will evolve. Maybe they are at some stage right now. In future, next 10 years, these things will evolve. Now, when we design 6G, we have to think not only today's requirement, but next 10 years, 20 years requirement, right? So some of those services which are going to become prominent are immersive XR, digital twin, massive MIMO, right? Ubiquitous connectivity. You could be on sea, you could be in, wherever mountains or terrestrial network everywhere, but you should have connectivity and fixed wireless access. It is so tough to dig down the road, put fiber cable everywhere. So not only, network between, between your mobile and the network, but even the backbone, can it be all wireless, right? So that is what the major goal of 6G from the services perspective, right? This is famous diagram. Most of us who work in this domain, when you search Google, this is the first thing you get, right? So I'll not explain much here, but what is new? What is new? We have seen this diagram for 15 years now. Limited version of that was there in 6G, 5G also. What is new? Three things are new: AI, right? Ubiquitous connectivity and integrated sensing and communication, right? These three are new. So, and this is also initial, so, the whole standard, who defines the standard are basically two bodies, right? There is one global agency, which is United Nations agency called ITU, which actually sets the requirement. What does it take for a technology to be called 5G or say 6G? So that comes from something called ITU, right? 3GPP is a body who actually makes the standard, submits to those requirements to be called as 5G or 6G. So for people who are not knowing this, this is the overall framework, how something gets to be called 5G or 6G, okay? Now, these are the set of requirements which I've kept. They are not final yet, okay? This was something which came few years ago. Maybe more refined version of it, exact version of it will come maybe after 2 years. And that's where, we will have the technology, right? But then what is that which 5G cannot do, right? What is that which requires 6G to happen, right? Just because every 10 years some new G has to come, so 6G is coming, or really, what is the problem? So 5G, the major thing which happened was the vision was very good, right? Lot of planning was done in what it should be, but when actual deployment happened or when the actual standards got developed, it was probably taken with not so discipline, right? Some examples here are that 5G is the one who came with many good concepts, right? Network slicing, something called FR2, right? Doing the millimeter wave, positioning, to be able to find your exact location, right? NR over unlicensed. 3GPP has been trying very hard to get into your Wi-Fi right? Everywhere we use Wi-Fi, but nowhere for personal at home setup we don't use, right? So NRU, right? Many features it came. Everything was there, but it was all very staggered, right? Ideally, what should have come from the very beginning? Only first beginning, if you remember the wheel chart, you had EMBB, low latency, and the massive MIMO. But what came in the first standard is, okay, just the broadband part. Then what everybody did, including the device and the network manufacturer, is just implement that one, and they called their devices or network as 5G. Many things which actually were the initial objective of 5G, they came in later phases, and by the time it lost steam. So today the scenario is we have the technology as add-ons, right? Not done from together, right? But everything is, not actually getting deployed. So we have the standards, right? But many things not getting deployed, right? So that is the problem. Right now, very good thinking is happening in 6G that let's not repeat those mistakes what we did during 5G, right? This time when we make this standard, let us clearly define what we want from the very beginning, right? And do not have too many options, right? Together, too many ways of implementing things, NSA and SA, right? In India, one operator is still doing NSA, another operator is doing SA, right? Many things like FR2 and all, not even done, right? Or sometimes done, but then taken back, right? So all those challenges, 6G, lot of thinking is happening right now, and that's where 6G standards are evolving. Okay, I'll not take much time here. My purpose here is not what technology came at what. The point I want to say here is that in industry or in 3GPP, how things happen is that they really do not take anything new just like that, okay? What has happened typically is people who worked in 3G, right, they would know that 3G initially, 5 megahertz, it supported only 384 kbps, right? But by the time, after 4 or 5 years, same 3G was supporting 42 Mbps. How was that possible? They tried to enhance the 3G itself with a totally new concept called shared channel, which was not there. Previously, only dedicated channel, common channel are there. So they introduced the HS, right? Maybe during the 3G lifespan, it was not so successful. But the same concept, because they tried and tested in 3G, became the base from 4G. Right? So that is one example I take. There are several examples of this. MIMO, if I ask you a question, when was MIMO introduced? It was introduced in 4G. That's what everybody thinks, right? But MIMO was first introduced in 3G. Maybe practical deployment did not happen much. But that experience 3GPP took, and from the 4G it became the base, right? Massive MIMO, if I ask you, many of you will say, oh, it came in 5G. But actually, massive MIMO was part of 4G in the later releases. Specification got developed, a lot of experiments happened, it came into specification, but in reality it happened in 5G time. Now, that is what the clue I want to give you. Okay, what will come in 6G is the clue here, that don't believe just what happened in the 5G beginning, right? Lot of evolution has happened in the 5G itself called 5G Advanced, right? Many technologies have been developed. All of them are candidate for 6G from the beginning. So very similar pattern I see here. Lot of innovations have happened. Those things will get enhanced during the 6G from the very beginning. Okay, this is how timeline. So just a brief step note. This is almost everybody knows, so I'll not spend much time. 3GPP right now is into release 20, right? So they have officially started the study of what should happen in the 6G, right? And during the 2027 and 29, actual 6G specification will come. And by 2030, we'll have the actual products, both network side and the. So that's what is the things going to span out in next 5 years. Right? This is 3GPP way of working. Basically, 3GPP, actually they don't say 6G or 5G every time. They works in the releases, right? And how it evolves is that, first version will come, then second version, more enhancement will keep coming. So 3G, when we say it is not just first release called release 99, it includes release 7 And lot of things changed from say UMTS to HSP. I gave example of shared channel concept. This shared channel concept in 4G became the base, right? So that's how it works. And these are the way various standard bodies and it is divided. So, okay. So is it that, okay, what is there in the standard, we simply implement? So many things are there. Do everybody implement? That is what we have learned very hard during the 5G. Specs have become very big, too many services, but in reality, what gets implemented is what is really needed. Because everything, development cost, including hardware, software, everything takes cost, money, effort of people, everything, right? What is there in the standard as it is don't get implemented, but what is really needed gets implemented. So that should be really the focus while developing the 6G standard also. Just for the sake of doing it, don't just make it big document, right? How 3GPP discusses, this is one example, many of you were there in Bangalore. This is how people sit together and discuss, right? And these are the items. What are they discussing? They are discussing these items, if you see, right? Right from very basic. In 6G, what will be the waveform? What will be the channel coding, right? And for around 6 items, some broad level discussions have happened, right? Some initial conclusion have happened, right? In summary, waveform, it is decided to use CPU FDM as base, which was the case with 4G, it was the case with 5G. Now that does not mean that new discoveries like OTFS and all will not be there at all. It is possible for certain cases, it may get introduced, but overall 3GPP will never want that, for everything you change it to OTFS, right? So that's where the, language is very written in that way that, okay, CPU FDM is the basis, but it is open to other waveform, right? So that's how things will happen. When we say channel coding, LDPC, polar code are going to continue, right? For AI/ML in 6G interface, I'll come to that, I have little. So for some little bit initial decision happened. Over next 18 months, these items is what 3GPP will be studying. And lot of consensus buildup will happen. And finally, at the end of 2007, when the real specification start, exact thing, how things should be done will happen, right? Okay. This is just an example that CPU FDM has been decided for the duplex. We have FDD and TDD, which has been the case for all these. Maybe similar will continue. Channel coding, we have gone from convolution turbo to polar LDPC. They are found to be good, so they are likely to continue. Related to modulation, 1024 QAM and 256 in uplink, these are also expected to continue. These are the initial, but there is a star here. So what was decided is that, okay, we do not know exact KPI parameters from 6G what ITU will ask, but for now, in the practical aspects, this is the level of modulation which performs good, right? Beyond that, if we go, there are problems. We'll see later, but right now, let us stick to this. So that's how the discussion happens. I have included many other, how data plane evolved, how RRC state evolved. You will see that, things are a little bit sometimes coming and going. So for example, 2G was just 2 states, right? In 3G, it became very complex, 4 states to save power. Then in 4G, again came 2 states because they wanted to simplify the specification. Then in 5G, they realized, okay, no, these states were really important. So something like that again should come back in 5G. So this is a forever discussion, and in 6G, for example, this also will be the discussion. Likewise, we can, when we work in 6G standard or something, we can evaluate for every aspect and then come to, okay, what will be the case. Very same case, for example, we have something called, everybody, it's a famous exam paper question, right, when we take the communication standard course. So we have, for example, okay, hard handover in 2G, then 3G had softer handover and so on, right? But actually, if you realize, software handover is nothing but ability to download from multiple base stations at the same time, right? Now, same thing in 5G. In the later releases, something in form of multi-TRP is coming back, right? Names are different, but concept is very much similar. How? So by understanding how things evolved, what were the problems when it was first done in 3G, right? If we have that history also as researchers, it will be really useful for us to understand what happened to that in the past and how can we take care of, say, while introducing multi-TRP in 6G, right? So that is the way, like, we have to analyze, never think, okay, something is very new and let's do it. No, there are some things of that sort previously tried, and that can act as our, checks and bounds, how we should be doing in the new standard. Okay. Probably this is one slide. I just want to say that, the basic purpose of whole network and mobile phone business to have a call and to download data have remained same. I was one of the fortunate one who started working in 2G, then saw the same network getting modified to support the PS data called GPRS, right? From there, if we see, right, the functions in the network have remained same, whether it is 2G, 3G, 4G, or 5G, and so the architecture. The how we implement part has been changing, and mostly right now it has been implemented like this. So instead, we used to have one base station, but now, for example, it is distributed into DUs and CUs, right? That's for better implementation, but overall architecture, if you see, and 6G is also not something very, overall the functionalities are going to remain same. Okay, what is the future direction? So I have taken around 5 aspects around which we will just discuss briefly what is going to happen, right? So 6G, as you know, okay, 5G had FR1 and FR2 as the spectrum. For 6G, what should be the new spectrum? It has been changing, right? 5 years ago, there was a different thinking when 5G just finished, right? So people were wanting to go to terahertz range. But then, lot of experience came with 5G deployment that as you go very high frequency, the cost of deployment of network is very high, because higher the frequency, you have to put base stations everywhere, right? For the majority of the use cases, the cost is exuberant. So because of that, 3GPP or industry wants to have some band wherein like it can have, okay, not need for installing base stations everywhere, so they can control the cost as well as have good coverage and higher speed. So considering that in mind, in 6G, new band, which is in between FR1 and FR2, is coming up, right? So something called FR3, right? How a band decides the technology, right? So the concept of, there is a concept of SCS, right? Or what should be the minimum unit of the frequency, right? So last two months ago, the discussion there was, okay, 5G gave too many options, right? So now because we are going to have 3 bands, let's limit in each band what can be possible SCS, right? So that's where, all these things are interlinked, and the common principle what came out during the social meeting is that in 6G now, because we have 5G experience, we'll have, it is written as 4 further studies, but this is the conclusion which happened 2 months ago. But you can see that people in industry want to stick to few options per band, right? So that will reduce the overall simplicity. It will make network simplicity, reduce so many options and signaling overhead. Right? Now that was about the spectrum. So FR3 is a new band, which is between, say, around 7 gigahertz. That is going to be the new one in 6G. For AI/ML in wireless, overall mood in industry is that, yes, it is the future. It will happen. For many things, standard need not to be there. It can be developed within the network or within the device. But for some cross-functional procedures, AI can be useful, but it would require some framework to come live, right? So 3GPP has come up with this kind of a framework, which is, say, 2-sided, one network one-sided, and UE one-sided, right? What does it mean is that where the model is sitting. So 3GPP and industry have also concluded that they will not be actually defining the model, right? But where exactly it will be sitting and what will be the framework, where exactly, how models and trainings will happen, that framework is where 3GPP will involve. One more thing which is decided is that in 5G, for these scenarios, already 3G AI/ML is used, right? Which is the basically CSI feedback for the beam prediction and for the positioning. Some of this framework and these use cases are expected to continue in 6G, right? And some more use cases, right? For example, these use cases will also be tried out in 6G. So in summary, AI/ML in 6G is going to be reuse the framework what is developed in 5G Advanced, reuse some of the use cases while continue to research on these use cases, right? This you see certain proposals from many companies. In all these areas of wireless, how AI/ML can be used will be enhanced. Massive MIMO, our favorite topic, right? Lot of things have evolved in 5G, but many things have not gone into real deployment, especially the case of multi-user MIMO, right? Theory is good, right? But it is not that fine level at the practical level. In 6G, aim is to make it successful, right? That is the aim, right? How can we do that? Massive MIMO implement in a true massive MIMO, right? Number of ports, for example, in 5G are still 32 or 64. Truly, it's not, right? So in 6G, from the very beginning, number of ports are going to be around 256. That's the aim. That was what everybody in that room, all the companies, network side, UE side, everybody was saying. So increase the number of ports, make MIMO energy efficient, do not turn on all the antenna elements all the time, but do it to save the power, and also make distributed MIMO reality. So in some form, multi-TRP has come in 5G, but truly speaking, nobody has implemented it. Lies in the standard, right? Because too complex right now. In 6G, direction towards massive MIMO is that learn from this experience and let's make it successful in 6G by doing all these three things, right? That's the direction for the massive MIMO. Now, coming the ubiquitous connectivity part, in 5G also, when certain private companies came up with non-terrestrial network, certain companies are having this solution already. 3GPP realized that let's make it a standard, because whatever some companies are doing, it's not scalable. So 3GPP added NTN, right? However, in 6G, the aim is that between TN and NTN, right, terrestrial network and NTN, how can we come up with a standard, unified standard which will cater to both, right? Challenges are many, like propagation delays, Doppler, distance, power. It's totally different between various kind of network. How can we make one single network? That is the challenge. And next 4 years, a lot of work is going to happen towards this direction. And 6G is expected to, you will not even know. Your phone will switch from satellite to terrestrial. That is the aim 6G is having. Regarding energy efficiency, a lot of things are tried. Same story happened even here. Energy efficiency was an afterthought in 5G. Many good concepts are there, right, for low power mode and so on. Even base station can turn off. There is an extra signaling in which network can turn on the mobile phone, right, wake up signal, right? Or UE can even tell to network, for example, now I need the data, you please turn on this extra base station. But none of them is reality. It's there in theory. In 6G, all these things are going to be practical. So with that, and one more last objective is integrated sensing and communication. So this is something, same communication, how it can be used for sensing and for the self-optimization also. So that is something real need, which is getting tried. So key takeaways, if I have to say, 6G overall aim is that how it can be unified architecture, even with considering so much diverse requirements, how it can be AI native, energy efficiency, ubiquitous connectivity, and cost effective. This aspect is very much important. And to contribute, my request to all of you is that apart from what you see from the research papers, also see what industry has a way of working, have a way of terminology for everything, massive MIMO and everything, right? To really contribute to standards, you have to also understand how practically things happen in the specification. That's where, when you join the industry meeting or all these 3GPP meetings, you have to adapt your proposals to this way, and that's how you can make it, we can achieve that goal. Initially, we had INAE goal, right? 10% of, patents we should have. To really achieve that, we have to adapt to how things works in industry, and we have to take care. Yeah. So, thank you.
Good morning to all of you. At the outset, I want to thank INAE team and IIT Kanpur, the professor, specifically IIT Kanpur, no, IIT Kanpur, and specifically Aditya sir for inviting me and presenting my talk in front of such a august gathering. So I will confine myself to the federative learning at its uses in 6G IoT and wireless technology. So first time this your term federative learning was coined by Google Research in 2016-17. After that, a lot of paper has been written in this direction. If you see nowadays, every year thousands of paper are coming in these technologies, and how to make framework for using this technology, federative learning technology in 6G. Many work is done. So, but till now it is at very nascent stage itself. Because of the nature of the problem itself is like that it is at nascent stage. So, outline of my presentation will be that I will first go through the what is federative learning and why we should do federative learning, what are the key challenges, and after that how we can use this technology in 6G, and what are the challenges to use these technologies, and after that what should be the future directions, and after that in brief I will recommend something. So when we talk about AI, artificial intelligence, then data has to play its key role. And when we talk about that the percentage of the work, then we can say that 80% work is of data only. If you have qualitative data, then most of your work is done. So, but the problem with the data itself that people do not want to share. Like in DRDO also and in defense forces, in tri-services if you will go, then definitely people are not willing to share their data and all other things. Like even if you will see the DRDO is working with academia, so when they ask data and all other things, then we also hesitate to share the data. So here only our federative learning can do significant contribution. So what is the concept of federative learning is that everyone is free to train their data on their local devices. After that, what they will do, they will share only the inference of that training to the centralized server. And after that, centralized server will do something like it can, in simple way, it can do the average of all the inferences, and it will send it to the again to the devices for next convergence, next iteration, and like that our algorithm will converge. So this is the concept, and if we are using this concept, then definitely data privacy problem will be solved. Like you have not to share the data, and security also, because if you are sharing the only inference of that data, then definitely one cannot do reverse engineering and find out the data itself. So at least your data is secure. And also one decentralized training also we can do. Decentralized training is done. So in federative learning also we can see that there is concept of centralized server does aggregating, and after that it sends its inference to the local machine. So what we can do here that every machine can also share the data. So we have not to send the data to the centralized machine itself. We can do local sharing also. So that bottleneck that can also be removed. And since we are dealing with the different machines have different type of data, different type of distribution of the data also there. So what data robustness will be there, and whatever you have trained the model, it will be very robust. So if you will deviate data from something to something, like delta deviation from the data will not challenge your algorithms accuracy and all other things. It will also like adaptability to the evolving threats. Like suppose somebody has sent that inference at one iteration, and in second iteration if it is sharing the inference which is totally different from that, then you can say that this node may be compromised and all other things. So it may also do the that problem also. So, and definitely for communication, we are sharing not the data, only inferences. So definitely our communication efficiency will be much more improved. So key challenges in the area of adaptive learning is that how to cluster the devices, like which devices should we cluster for the taking part in the training process. Data heterogeneity will also play its role, because generally we assume that if we are catering large number of data sets, then non-IID will also become IID and all other things. But if there is a non-IID data, then and you are doing in the wireless communication area, then definitely what will happen that this your convergence will take a lot of time, and it might happen that convergence may not happen. Resource constraint, like every devices you are thinking that at least it should do some computation. Like it should have some computation, like not IoT devices, like IoT devices. By concept, it may be IoT devices, but it has some computation capacity also. Also, how you route the model parameters, like if your cluster is far away from the centralized server, then how to route it properly and all other things. And we have seen that this your adaptive learning is not very much robust against the state-of-the-art attack. Like there are many attacks which was mentioned by Partha Pratim Chakravarti sir, that there are evasive attack, there is data poisoning attack. So if you will change some data, if you will put some noise in that data, then how to tackle with those things. So these are some challenges. Denial of services may happen, that your device or link should be over flooded with non-constrained data and all other things. So that is also one problem. So sir has already told that what are the use cases and all other things in 6G and all other things. So 6G mainly, if you'll see that the main thing is that it's concept of autonomous vehicle and all other things. Autonomous vehicle, like suppose our model has learned the basic things, but suppose it has to do some changes at runtime and all other things. So it is not possible to send every time data to the central server, and from central server it will do the training and send back to the autonomous vehicle and all other things. So autonomous vehicle will collaborate each other and train the whatever the real scenario occurs, like that it will train the model itself. So that is one advantage of if you are using the adaptive learning technique. Also, like augmented reality, virtual reality, we are going to use in 6G and all other things. For that also the same thing happens, that if any environmental change and all other things, how to cater those things. Like in AI and all other things, our data is data is a centralized server, and we are doing all the processing at the centralized server itself. So, but here we have done the training, basic training we have done. Whatever the changes are coming, that we will cater with the use of federative learning. And when we are talking about the smart cities and IoT sensors and all other things, then everything should be connected to everyone. So some devices may be of maybe not very much can do this can do computation and all other things. So how to deal with these things, we have to think over. Definitely UAV we are talking about, then UAV, swarm of UAVs are there. They can train the data on the air itself, and it will take the decision also. So that will be the one use case of this in defense area for federative learning and all other things. And integrated sensing and communication, as already mentioned by our previous speaker, that integrated, same thing can be done by sensing, and as well as communication also can be done by using that devices. So definitely, like using this technology is very promising. It is looking very promising, but how to use it in 6G framework and all other things, like using AI itself is a big problem. Now you are using federative learning framework and all other things. So we have to make one framework for that. So for making that framework, if you will see that 2023 to 2025, I think at least 20-30 paper has come that how to implement those federative learning things at each physical layer, data link layer, everywhere, how to use it. So we should go through that and find out that how to accommodate those things into 6G technologies. So because definitely in 6G we'll see that the scalability will be more. Like it is not like 20 to 30 devices are connected with each other and doing training and all other things. So how to deal with that? So one concept is like hierarchical federative learning can be done. Low latency and real-time, near real-time performance, like we cannot wait, like communication may be faster, but computation may take time. So how to deal with those problems and all other things. And also that parameter which we are sending definitely has some bits and all other things. So how to compress it so that only even inference of inference will go, and that some mathematical things is required. And heterogeneity management, like heterogeneity will not be on the data side itself, it will be on the devices also. Like some devices are edge AI devices, some devices merely AIoT devices which will only broadcast the data and all other things. So how to deal with those things? That is the one key to ponder upon. And energy efficiency, like definitely, like if you are putting that thing into the wireless communication and all other things, there will always be a energy constraint things which we have to think over, like battery issue and how we route the data so that minimum battery will be consumed. So that type of things we have to think. Reliability and robustness is one big problem with any AI and all other things. Like if you are changing the data and if you are adding noise and all other things, how to deal with those things? So that is the main problem. Like even if your algorithm's accuracy is less, but if it is dealing with the poisonous data very well, then that should be taken part into the federative learning things and all other things. Huh? Okay, so that thing we have to see. So these are the requirements for that how to integrate with edge computing, cloud and network infrastructure. And there should be one standardization technique, like how to standardize that thing to included in the 6G technologies. So future direction of research will be like joint communication learning co-design, like efficient model update compression, like I have already told, and asynchronous, like some devices may leave you in between that. So it should not affect your convergence of the algorithms. That we should also take part of that. So privacy, security mechanism beyond basic FL, like some people are using that blockchain technology also in FL and all other things. So that we should think about. Incentive mechanism, like why device should participate in your federative learning things and all other things. So, and lightweight FL, like we should not depend upon only on the like conventional AI algorithms. We should make proper FL algorithms, which is lightweight CNN models, which we have made some improvement we have done in that. So that type of things we should think. Like we should not think like large language model and all other things. If you are thinking about only in wireless things where devices are not connected with any power and all other things, then so I will not take much more time. Like what will be the recommendation? Like multi-tier federative learning architecture may be adopted for including FL in 6G, since it has shown the promising result. And more research should be done on non-IID data and all other things, how to tackle with non-IID data. That is like I have already said that and more research and funding is required in cognitive computing. Like people are saying that LLM is also using cognitive computing and all other things. Definitely it is using. But for using cognitive computing, it is doing millions of other computing also. So what we are doing in this AI and all other fields is that a little improvement we are doing, but for that we are taking much more energy, much more computation and all other things. If in this way we will go, then how far it will go, how you can use it in real field scenario, that will be the one challenge. Like I am talking to you, if I am concentrating on Chaturvedi sir, then I am concentrating on Chaturvedi sir, all things have just vanished to me. So that type of computation is required. That is only cognitive computation. Cognitive computation means that only. It does not mean that you are doing millions of computation here and there, and after that you are saying that this is cognitive computing and all other things. So that is not because human has non-deterministic way of dealing with the algorithms and all other things. So how to deal with that things we should take care. And more research should be required in AGI, because AI we are doing, but how to put only inference on the boards and all other things, that thing we have to think. And AGI, many private vendors are doing, but they have made IP, so you cannot play with that IP and all other things. So we have to do basic research and all other things, like how to put, because we have trained on floating point numbers, and after that how you will deal with the fixed point numbers and all other things. So a lot of things are there, so we should ponder upon that. So that's all. Thank you very much.
So I'll talk about essentially next generation Wi-Fi or next generation wireless LANs. And the case I'm going to make is there's a lot of excitement and hype also about 5G, 6G cellular systems. I myself am a cellular system designer. But in parallel, I think there's also a revolution taking place in Wi-Fi technology. And Wi-Fi will just be as much of an integral part of 6G wireless access as cellular systems themselves. So what I'd like to convey to you through my talk is it's a very exciting area of research and essentially yet another backbone in wireless access. So if you look at Wi-Fi, I think you probably have a couple of access points here. They're probably hidden somewhere. It's central to providing connectivity to the public in enterprises or commercial places. And not just indoor coverage now, people are using it also for outdoor coverage. So it's there everywhere. And secondly, a significant portion of the cellular traffic itself is downloaded onto the Wi-Fi network so that you can decongest the cellular network. So it's essentially critical for providing wireless access today. And the expectation is that it will continue to be critical in next generation wireless itself. Now, if you look at evolution of Wi-Fi over, say, the last 2 decades, it's undergone a fairly dramatic revolution, or evolution, I should use that word. About 2005 vintage, there was this standard called 11N. These acronyms don't have any meaning to them, so just take them as I throw at them. Don't try to open the acronyms up. There is really nothing you can do about it. But there was a standard 11N. Several of our phones probably still support 11N. They were talking of, of the order of tens of megabits per second type data rates. Then came Wi-Fi 6, which is currently getting deployed now more and more. I still don't have 11AX access point in my house. I have a Wi-Fi 5 AP, but soon I'll probably be getting 11AX AP. If you look at 11AX, they're talking of now much higher data rates of the order of gigabits per second. Just very recently, Wi-Fi 7 got standardized. Again, there's an acronym for it, 11B. Don't worry about the acronym. They're talking of gigabit per second data rates. And work on the next generation of Wi-Fi called Wi-Fi 8 has just started. Standardization efforts have started, and they're now talking of, you can see the numbers, up to 100 gigabits per second data rate. So there's a dramatic change in what Wi-Fi was and Wi-Fi will be. And over the talk, you will also see it's not just data rates. Data rates are in some sense a marketing number. One should always take them with a pinch of salt. It's also the spectral efficiency. How much information can you pump through the channel per unit bandwidth? Also the latency. Those of the items also have been improved quite a bit over the evolution of Wi-Fi. Okay. Now, what is the secret behind the success of Wi-Fi? You can ask, why is it so prevalent? So fundamentally, Wi-Fi works in the unlicensed shared band. It's called the ISM band, Industrial, Scientific, and Medical band. And you'll hear these terms for 2.4 gigahertz, 5.5 gigahertz, and there's also 6 gigahertz. India has not yet operationalized it, I think, but it'll come sooner than later. And the fact that you're operating in an unlicensed band means that you don't have to pay spectrum licensing fees to the government. And if you've seen the news, you know how much it costs. I mean, a cellular operator pays several thousands crores for spectrum access. You just don't have to pay that. Now, that makes the system fundamentally cheaper. The second thing is, and this is a point I'm going to elaborate on as I go further in the talk, is that by its very design, it's a very distributed system. Every access point does its own thing. Every user or station does its own thing. There's not much coordination. There's a little bit of coordination, but not much. So what that means is we've got much, much cheaper devices. So for example, if you look at a cellular base station, the cost of a cellular base station can easily be several $1,000s. But if you look at an access point, I can buy it and put it in my home. So it's like tens of dollars to at most $100. So it's much, much cheaper. And there's a reason why it's much cheaper, and you'll see that as I go along. Now, and of course, it's very easy to deploy. You can just pretty much unwrap the access point and plug it in, and you're ready to go. Now, of course, this comes at a price. There's no question about it. A cellular system is very centralized. The base station controls everything, who transmits, when, with what power, and so on and so forth. There's a lot of central control, and there's a reason why there's centralized control. You get much more bang for the buck. It's very expensive to use the spectrum, therefore you use it very efficiently. In Wi-Fi, you inherently have to be resilient to interference. Because it's an unlicensed spectrum, it means that anybody can interfere with it. For example, your Wi-Fi transmitter will get interfered with the access, with your microwave oven. It'll get interfered with your Bluetooth device. There can be a lot of other interferers that can show up. You've got to be interference resilient in your very design. Now, second, because it's unlicensed, you've got to share it with everybody else. Sharing means that you cannot blast a lot of power out. So there are constraints on how much your transmit power can be. There are constraints on how much you can focus your transmit power. That's what we mean by antenna gain. Now, to deal with this kind of coexistence with this sharing, inherently the Wi-Fi standard or whatever technology goes into the Wi-Fi standard has to use techniques that are compliant with these kind of requirements. So the digital modulation techniques that we use are compliant with this interference resilience type design. Secondly, the protocols that are used in the Wi-Fi standard, and this is again something elaborate on, this is going to be the heart of the talk, are also designed to be resilient to interference. For example, and also they are designed to ensure that you don't cause too much interference to the others. So Wi-Fi, for example, uses what's called carrier sense multiple access, which means that you sense the channel, and only if you find the channel to be idle or nobody else is transmitting, only then do you transmit. So it basically means be polite, don't just barge in. And if the idea is to prevent collisions, or essentially two people transmitting and interfere with each other. So there's a lot that goes into this to make it happen. Okay, and so what I'd like to do to kind of just elaborate on these points a little bit is just in a slide or two give you a flavor for what I think is the heart and the beauty of the Wi-Fi protocol. And it's a very simple idea. Essentially, how does a distributed system work in a wireless system, in a wireless channel? So essentially, the idea that Wi-Fi uses is randomization. And the randomization is as follows. So basically, say I have a packet to transmit. Somebody else also has a packet to transmit. We do not immediately jump on the channel and transmit. Because what would happen is then we would both transmit, our packets would interfere with each other, or what we say, they collide, and really nobody can make sense of the packets that were transmitted. So that's not what happens. So what happens is each node randomly decides when to transmit. And the way it's done is as follows. You pick a timer, as it's called. So one number between 1 and 64, for example, randomly. And then you set your timer with that number. And then you slowly count your timer down. Every time you measure the channel, if you find that the channel is empty or idle, you count it down. Okay? However, the channel is busy, which means somebody else is transmitting, you freeze your timer. Okay? That is your carrier sense multiple access in operation. And the idea is the moment your timer hits 0, boom, you transmit your packet. Okay? Now you can see that different users would have used different timers because they're chosen randomly. Therefore, the users would end up transmitting at different times. You already have got randomization taking place. Now, despite all of this, you can easily imagine a scenario where two users would have chosen the same timer. It's entirely possible. Well, you've got only 64 values, for example. Now, what happens in that case? Both of them would indeed transmit at the same time. It's a distributed system. You cannot tell somebody, oh, don't transmit, wait for the other guy to transmit. Nobody really knows what's happening. So you would transmit your packet. So would your other person whose timer is expired. And the packets would therefore collide in the air. Now, what do you do in that case? Both of them again back off, choose new timers, and then go through the whole process again. And in fact, in Wi-Fi, what they do is they slow you down if you collide, which means you would double your windows. So if you chose 64 the last time, 1 to 64, now it will be 1 to 128. If you happen to choose 1 to 128 the last time, it will be 1 to 256 in the next round. So they slow you down so that these collisions don't become too frequent. Because you can clearly see collision is a waste of resources, it's a waste of transmit power, it's a waste of transmission opportunities. So this is how Wi-Fi works in a nutshell. It's a very simple protocol, but it's scalable, which means as the number of nodes increases, you can actually show that the protocol doesn't collapse. It'll saturate out and give you some performance. And clearly, it's distributed. Okay? And it adheres to the carrier sense multiple access principle that's required of anybody who operates in the ISM band. Now, things can go wrong. And here's one example of how the system is engineered to deal with things going wrong. So it can so happen, I said you must sense somebody else's transmission. And if the transmission, if you find it to be the channel to be empty, then you transmit. But it can so happen that even though somebody else is transmitting, you may not be able to sense the transmissions. For example, I show it in the cartoon here. There is a wall between the two transmitters. Okay? Think of that transmitter operating in some other room. I'm in another room. So even though that person is transmitting, I will not sense it, or the signal is too weak for me to make sense of it. Now, in that case, you are still merely counting your timers down. And when your timer becomes 0, you will transmit on the channel. And the problem with that is then the second person would also transmit, you're also transmitting, and therefore a collision will happen. So this is what's called a very famous problem called the hidden nodes problem in Wi-Fi. So there are protocol mechanisms meant to deal with it also. And the philosophy is very simple. When you send a packet, it's a big fat packet, several thousand bytes. And if a collision happens, you lose all the several thousand bytes. So instead, you send a small packet. It's called a please let me transmit packet. It's called the request to send packet. And if that packet goes through, then the access point tells everybody, hey guys, this guy is going to transmit. Please back off. Nobody else transmit. And then you're cleared to send, and then you transmit. So there are all these mechanisms built into the protocol to make it distributed and to make it work. So now, till now, what I've spoken to you about is the conventional Wi-Fi MAC protocol, 11N, about 2005 vintage protocol. Now, if you look at Wi-Fi now, from 11N 2005 to 2025, it's undergone a lot of evolution. So there have essentially been 3 generations now that have come. And what I'd like to do now in the next about 10 minutes is explain to you some very key features of these protocols and also tell you some work we've done in this space. So the version that came is Wi-Fi 6. Wi-Fi 6 deviated in many fundamental respects from the conventional Wi-Fi MAC protocol and explained to you. It introduced this new feature called hybrid access. I said everything is distributed in a Wi-Fi system. It's not like a cellular system where the base station controls everything. In Wi-Fi 6, they said, you know what, some amount of control is needed if you want to really use the spectrum efficiently. So Wi-Fi 6 introduced this thing called hybrid access, and I'll explain to you in a minute. It also used multiple antennas much more aggressively. Now, multiple antennas are great because essentially what you can show is if I have multiple antennas, you have multiple antennas, then I can send multiple streams of data to you in parallel, use signal processing to essentially separate out the different streams, and therefore get essentially much more data rate through better spectral efficiency than conventional systems. They also use something called orthogonal multiple access or orthogonal frequency division multiple access. Essentially, the idea is take the whole bandwidth, 20 megahertz, 80 megahertz, break it into small chunks, and then allow each user to access a small chunk. You don't have to access the entire 20 megahertz. And the beauty of the setup is, and I won't be able to prove it here on this talk, is when you operate on one small chunk, you do not interfere with anybody else who's operating on any of the other small chunks. So essentially, the system's transmissions are orthogonal to each other. So this was, this played a big role in Wi-Fi 6. And the other trick we always play as wireless system designers is, A, we increase the bandwidth. So because you have more bandwidth, you have a fatter pipe, you can pump in more data rates. But also I guess what the word I should, density with which you send information, or essentially the number of bits per symbol that you send out, is also increasing from one generation to the other. So in Wi-Fi 6, they went up from 256 QAM, which was able to send 8 bits per symbol, to 1024 QAM, which was able to send 10 bits per symbol. It doesn't mean you will get 10 bits per symbol all the time. Your stars have to be aligned. You have to have a very good signal to the access point. Only then you can go up to 10. But you still can go up to 10 if the stars are aligned. Now, if you look at the next generation of Wi-Fi, Wi-Fi 7, they took all of this in, yes, and they added more things. So one very interesting new technology, we are just beginning to look at it now. It's called multi-link operation. And I'll explain to you in the next slide, so I won't describe it now. And they jacked up again the density of information from 10 bits per symbol to 12 bits per symbol. So again, you can keep increasing the data rates as you go along. There's discussion now in Wi-Fi 8, where now, so far what I've spoken is one access point perspective. Now they're saying there are multiple access points. These guys should all collaborate with each other and make sure they don't interfere with each other too much. So there's inter-AP coordination that's now being introduced in Wi-Fi 8. So lots of things are happening as we go along. And the goals of these are to increase your data rates, but also improve your spectral efficiency. When I mean spectral efficiency, I mean how many bits per second you can transmit per unit bandwidth. And a cellular system designer would actually say bits per second per unit bandwidth per unit area. That's really the performance measure you care about. And of course, latency. And what we've been doing in our group over the last, I guess, 5 years or so has been essentially trying to understand, when you take all of these features together, what is the net performance of these systems? Do they add up? Or are there diminishing gains? How do you optimize their performance? And also, of course, as researchers ask the next question, what's beyond these technologies? So that's really where the interesting part is. Okay, so let's look at, I'll talk to you about two of these technologies, hybrid access and multi-link operation. So hybrid access is there if you buy an 11AX AP. It is there in principle. Some APs don't yet implement it, but in principle, it's part of the standard. What I really like about this is Wi-Fi beginning to accept the fact that pure distributed control is not good. Centralized control to some extent is needed. So what Wi-Fi 6 did, and try to contrast the protocol I discussed with you, 5 minutes back, was what it did was took the whole bandwidth and broke it into small chunks. So here are the 4 small chunks that I'm showing you here. Ignore the labels for now. And so these are called resource units. Okay, so 1/4 of the bandwidth. And one user can transmit on a resource unit. So in principle now you can support 4 users in parallel as opposed to just 1 user. So that cuts down on the latency. And what now happens is the AP has complete control over what happens. So the AP specifies this resource unit is for this user, that resource unit is for another user. So now the AP begins to schedule users. It's not just timers and everything. But there is a catch here. The AP needs to know who has packets to transmit, who doesn't have packets to transmit. Nobody's going to tell the AP what's happening. So the way that happens is, just like in conventional Wi-Fi, there was random access. Everybody set timers and transmitted packets when the timers expired. That still happens here. So the AP sets aside some resource units, saying, hey guys, these resource units are for the guys, for the stations I have no information about. You please fight it out, transmit your packets, use random access, and send your data. Once I listen from you, once I hear your packets, I will then start scheduling you out so that after that there will be no collisions. So what hybrid access is, as the name suggests, is a mixture of random access and scheduled access. And what our results were able to show very recently, we submitted, was that once you start merging both random access and scheduled access, you can beat conventional systems because your system becomes much more spectrally efficient, and therefore you can get much better gains. Of course, system design becomes a question. For example, you can ask the question, how many resource units should I set aside for random access? How many for scheduled access? Does it depend on the number of users? And so on and so forth. So all of these design questions have to be answered as you build these systems. But fundamentally, it gives you the capability to now go well beyond legacy systems. Okay, so let me talk to you about multi-link operations. I'm moving to now the next generation Wi-Fi that will come probably in our homes in 3 to 4 years from now. And that's multi-link operation. Everything I've told you about right now is one AP, lots of users on one single link. One link meaning 2.4 gigahertz. But now let's say I said, ISM band consists of 2.4 gigahertz and also 5 gigahertz. So now in multi-link operation, what they're saying is the AP can operate on both the links simultaneously. And so you can see that in the cartoon here. There are 2 links here. And it will simultaneously transmit on both the links. It will potentially simultaneously receive on both the links. And on each of these links, you've got what I described to you before, MIMO, OFDMA, hybrid access, all of that thrown in, okay? But the thing is, you can now do multi-link operation. Now, why would you want to do that? The benefits are obvious. The AP is able to push data much faster because it has access to 2 links. It can receive data much faster because it has access to 2 links. There's a latency benefits and so on, okay? Now, one of the important points that comes about, one of the important points that comes about is when you have multi-link operation, what sort of design rule should you use? When should I transmit on 1 link? When should I transmit on 2 links? How do I still ensure that I satisfy the requirements of operating in the ISM bands? So all of these questions are really where the interesting research problems lie today, and several of them are rather open. In fact, we just submitted a paper last week on this whole problem. So it's a very new area and very interesting new features throwing into Wi-Fi. Okay, so far I've spoken to you about 7 minutes about what is there today or what will be there almost tomorrow in Wi-Fi. Now, the last 5 minutes I'd like to speak to you about speculative technologies. What can be there in Wi-Fi? I don't know, Wi-Fi 9, Wi-Fi 10, I don't know. But what is the future of Wi-Fi? So one technology that I really like and something that we worked on is called full duplex radio. So let me just spend a couple of slides on discussing what full duplex radio is and why it's an exciting technology for Wi-Fi. So everything today, regardless of what the branding is half duplex. What does half duplex mean? It means the following. In this cartoon, you'll see 2 stations, the blue and the yellow station. At any point in time, the access point can either receive from one of these stations or transmit to one of the stations. So it can either receive from the blue or transmit to the yellow, but it cannot do that simultaneously. That's why it's called half duplex, okay? What full duplex is saying is, no, this is not smart. We should be doing both simultaneously. So I should be receiving from the blue guy and transmitting to the yellow guy. It's obvious it will lead to better usage of the wireless spectrum because you can see now there are 2 communication links happening in parallel. So it's kind of like a no-brainer to do full duplex. Now, the reason why full duplex is still not used today, there's a reason for it. It's not like people didn't think of this 20 years back. It's an obvious idea, but technologically it's extremely hard to pull this off. And the reason why it's extremely hard is this, the reason for this is called self-interference. So when you transmit a signal, you typically send at the rate of a watt. Roughly 1 watt is your transmit power. When you receive your signal, your receivers are designed to operate at essentially tens of nanowatts of received signal power. So what you have is a transmit signal that is 9 to 10 orders. 9 orders means 1 billion times stronger than your receive signal. Okay, so even if a small portion of the transmit signal, when I say small, even 1/1,000,000th of the transmit signal somehow leaks into the receive circuitry, it can completely wipe out your receive signal. It will drown out your receive signal. You can see that because you've got 9 orders of magnitude. Even a 1 in a million is enough to finish your receiver. Literally your amplifier will burn. So what you need to do to be able to implement full duplex is be able to cut down the transmit signal leakage by a factor of 1 billion or even 10 billion or more. Okay, that's really where the technological challenge was. And until 2010, if you had said, is this possible, I would have laughed at you and said it's a fairy tale. But now there are prototypes. Several groups, UCSD, Stanford, there's even a startup now that have shown that it can be done They use a mixture of hardware and software algorithms, but they've shown that you can achieve cancellation of the order of 100 dB. We measure everything in dB, that's just the way wireless works. 100 dB means 10 billion. A factor of 10 billion can cut the interference down. And therefore now it is indeed possible to do full duplex. So it's a technology that is going to come sooner than later. In fact, this is already beginning to get traction, not in the Wi-Fi space, but in the cellular space, in the 5G standard, what is called Release 18. They're talking of not exactly the full duplex that I spoke about, but a simplified version of full duplex. It's called subband full duplex, SBFD. So the idea is, even if I can't transmit on the same band simultaneously, I'll be able to transmit and receive on very, very close bands simultaneously. Okay, so the beginning to get there. The gap was this, they've shrunk it to this. Hopefully very soon it'll become like this. So there's subband full duplex. It's, I think it's almost standardized in the thing. There's also, in the context of 6G cellular, there's also talk of in-band full duplex. Of course, there's a lot of resistance to this because the hardware becomes much more sophisticated, but sooner than later it's going to happen. In fact, there was a full issue dedicated to full duplex communication in this very prestigious journal called the Proceedings of IEEE a couple of months back. All the papers were entirely on full duplex because they know it's a technology that's coming. Okay, so at least hopefully I've got you excited about full duplex. And so now let's talk about full duplex in the context of Wi-Fi. This is what this talk is. So now let's assume we've solved the self-interference problem. I've got fantastic hardware, I've got fantastic software, everything is working. Now, is it a no-brainer to introduce full duplex in Wi-Fi? Turns out no. There are still very interesting challenges that need to be overcome. The first challenge is the CSMA protocol of Wi-Fi that I discussed with you inherently will prevent full duplex from operating because it will never let two people transmit at the same time. But in full duplex, you want multiple transmissions to happen simultaneously. For example, the transmitter here would talk to the access point, and the access point would talk to some other node. They're two simultaneous transmissions. So you somehow have to change the Wi-Fi protocol itself if you want to leverage full duplex. Second thing is, even after you've solved self-interference, there's yet another new problem that comes, which only protocol design can solve, and that is called cross-link interference. So let me give an intuition about the problem. So say the transmitter is transmitting to the access point. Some of its signal will leak through to the receiver because wireless is a broadcast medium. When I talk to you, my signal will also go there. So there's this interference that now comes from the transmitter to the receiver. So if the receiver is receiving a signal from the access point, it will get interfered with by the cross-link interference from the other transmitter. And what this means is your signal-to-noise ratio comes down, your data rate will come down. In fact, there are studies we've also shown that if you're not careful about cross-link interference, you can actually get worse performance than even half duplex. Okay, so which means you're better off just not doing full duplex, period. So you've got to be very smart. It's a very powerful capability, but you've got to design protocols around it to be able to leverage it. How much time do I have? 2 minutes? Okay. So, and so I'll skip the part about protocol design. I had a slide on it, but I'll skip this part. So it turns out one can indeed design protocols and show that you can actually exploit that capability of full duplex. And I know I'm going to glitz over this, but I'll just show you something. So this is some measure of how much throughput you can get normalized as a function of the packet length. Turns out as your packet lengths become longer and longer, your overheads associated with the protocol decrease because you spend some time waiting, you spend time for your timers, all of that takes lesser and lesser fraction of time, so your efficiency improves. And we were able to show in some topologies of the network, you can actually get close to 2x benefits if you use full duplex. But in some topologies. There are other topologies where we are able to show that full duplex will not give you the promised 2x gains. The gains can be lower or non-existent also. So it's very much system design dependent. Okay, let me skip that and let me try to wrap up. So essentially, I think the message today I had was, I think Wi-Fi is an integral part of 6G wireless access. And I mentioned 6G because 6G is really the next thing that's going to come. It'll remain an integral part of 6G wireless access. There are several significant enhancements that have taken place to be able to position Wi-Fi where it is now. The enhancements are at the physical layer. When I say physical layer, I mean the modulation techniques, but also at the medium access control layer or the protocol layer. And all of this together is what gives you the benefits. And I spoke about some of the technologies like multiple antennas, orthogonal frequency division multiplexing, hybrid access, multi-link operation. There are many others I've not spoken about. In fact, some of them are questionable. It's really not clear if they give gains, even though they are in the standard. But these things we do see really leading to advantages. And if you look into the future, I think clearly there are new technologies that are coming in. I mentioned inter-AP coordination that will make things better, more efficient. But also I think one aspect that I've really not covered in my talk is new applications of Wi-Fi. I think, we all use Wi-Fi for downloading data, for streaming, all of that. But Wi-Fi in an industrial setting, when you use it in industry automation, I think it's a much more difficult environment to work in, because now I have to meet strict quality of service constraints. If I'm running a control loop, I can't say, oops, I missed your packet, just can't afford to do that. So can you actually use a distributed protocol or a distributed mechanism like Wi-Fi to support critical applications? It's a very interesting question. It'll eventually happen. How we get there is really the question. So a lot of very interesting problems. So with that, I'll stop. This is my group, and we basically work on wireless communications. Design, modeling, analysis. And if you're interested, there's a QR code. You can look up the papers. And there's also a YouTube channel, but these are technical talks, 20 minutes to 40 minutes, not 2-minute TikTok videos, but they'll have very detailed discussions of what I've said. Thank you.
Hello everyone, very good afternoon to all of you. I welcome you to this next session, session 2A under theme 1, that is Intelligent Systems. The title of the session is AI and Data Science, and our session chair is Professor Nishal Kumar Verma, who is a faculty member, a professor in the Department of Electrical Engineering here at IIT Kanpur. I give a warm welcome to Professor Nishal Verma, who is over here. Thank you very much, Professor Nishal Kumar. And Professor, just a brief bio. Professor Nishal Kumar Verma is a professor in the Department of Electrical Engineering at IIT Kanpur. His research interests are in artificial intelligence, machine learning, cyber physical systems, computer vision, industrial automation with interdisciplinary applications. A prolific researcher, educator, Professor Verma has significantly contributed to the advancement of AI/ML driven techniques for pattern recognition, emotion recognition, image dehazing, prognosis, life prediction of machines, etc. With over 2 decades of academic and research experience, he has published extensively and holds key editorial positions in top journals and conferences in the area of intelligent systems and data-driven technologies. His research group has actively collaborated with national and international institutions promoting interdisciplinary innovation and technology development. Professor Verma currently serves as the chairman of the IEEE Computational Intelligence Society Chapter Uttar Pradesh section, and has been instrumental in organizing several major scientific events. So he's committed to advancing indigenous AI innovation, and Professor Verma's vision is to leverage intelligent technologies for societal transformation and national development. With that, I welcome Professor Nishal Kumar Verma to chair this session too. Thank you. Thank you very much.
Very good afternoon. I hope you had good food. First talk is in this session is AI as skilled engineering assistants, opportunities and challenges, by Professor Amrutur Bharadwaj.
Thank you for inviting me to give a talk in front of this very august audience. So I was scratching my head as to what I should talk about. And there's always a balance between going deep into one particular topic versus keeping it a little bit general and at a meta level. So I thought maybe there's a diverse audience out here. So I'll just keep, I'll just talk some things about, kind of the ongoing, shall we say, tsunami of AI and how it impacts engineering. And so that's why I kind of titled it NJI for Skilled Engineering Assistants. So you have all heard of Gen AI, which is generative AI. So NJI is AI for engineering. Right? And so let me kind of articulate what I feel as some really exciting opportunities for us in this space. So first I want to start off with a really, kind of summarizing some key insights from a very recent talk by, I would say, one of the pioneers in, practical AI. So you can look up on YouTube this person's really interesting talk on the 3 key ideas of AI, which I just wanted to kind of summarize out here because it has an impact of how we will do and go about using AI for our engineering work, right? So the reference is below out here. So of course you can search on Google and you'll get his talk. So the first point Jason makes is what he calls verifier's law. And what it means is that the quality of an AI model is essentially related to how easy is it to verify something. So if you have some data sets or some examples which is very easy to verify, then you can train an AI model to actually do that job very well. For example, let us say training an AI to play Sudoku. Right? So given a solution, you can check whether the solution is correct or not very quickly. And so you can actually train AI to play Sudoku very well. Of course, in addition to that, you also need, for many domains, you also need data which is not easily available, but that is the other thing. You have enough data and you have an ability to quickly check what you're doing is correct or not, problem is solved. Second really interesting point he makes, and which we are seeing now, unfortunately for us humans, intelligence has become a commodity. What does intelligence mean? Intelligence means the ability to solve problems. Okay. So that is becoming a commodity, and I think this is something which has a huge impact for how we do things as we go forward. So as you know, now you can, it costs very little to actually solve some really complicated problems, making a call to some of these AI models on the web. Of course, what it also means is that because it's becoming a commodity, it's also getting democratized. Now people have the ability to access intelligence through their smartphone, right? And that also again has a huge implication for people and society. The final point, again, it's related to the first point, is the jagged edge of intelligence. What essentially Jason is saying is that the intelligence is not uniform across all disciplines. And it is not surprising. It's related to the amount of data and verifiability for different disciplines. Advances are much more in areas like game playing, in computation math, etc., right? Whereas some of the other areas where the availability of digital data is sparse or it becomes very difficult to check, the models are not yet there. So what does it mean for us as engineers in the engineering profession, right? Whether we are practicing engineers, whether we are teachers, or whether we are learners. Right? So one kind of mission goal I would put out there is, I call it AIGE, right? Can we create an AI-enabled generalist engineer which can solve any problem, any engineering problem? Right? Any engineering-related task, we should be able to ask the AI generalist engineer. Is it possible? My opinion, yes, I think it is possible. And I think it will get done, and people are working on it. Of course, for us is, what does it mean then, right? For the engineering profession and engineering education. Okay. So the rest of the talk, I'll just try to kind of articulate at least my perspective, and I'll be very happy to hear your views and opinions at the end of the talk. Hopefully, we can have an interesting discussion. So firstly, why do I think it is feasible to build this AI generalist engineer? Right? So one of the things is that the engineering always stands on science, right? And science which is usually well understood. So we know what is going on. Of course, it might be difficult to, at least it would have been difficult to kind of fully predict what happened, but the science is known, right? For example, you want to know the electromagnetic compatibility of the product you have made, or what kind of electromagnetic interference it will create. The science is Maxwell's equations, right? It's well known, like 100% we know. You solve the equations, you put the initial conditions, you know what will happen, right? Batteries. Right? Well, we engineer batteries. It's based on science of electrochemistry, science of electronics, science of heat. Right? All these sciences are known. And so the second thing is that fortunately, the engineering practice in the engineering domain, there's a lot of documentation. Engineers document things well, good engineers. There are, of course, large numbers of textbooks, research articles, manuals, technical reports, user guides, data sheets, so on and so forth. Right? So there's a lot of data which is in the digital domain. And when we do something, we can also check whether is it done correctly, which is the verifier's law, though it may not be easy all the time. And that's because many of the engineering disciplines have actually created simulation environments, simulators, which are very accurate. And you can use, people use them, engineers use them for design space exploration, for validation, for a lot of what if, etc. Right? For example, in the VLSI area, which I used to work in before, very high quality, very accurate simulators are there for circuit simulation and so on, which ensures that the chip you design usually comes out working the first time. Many tools, COMSOL, HSPICE, ANSYS, etc., are there for doing all kinds of engineering, multiphysics simulations. Okay, so that is case for saying that, look, yes, I think it is possible to make this, but what are the roadblocks for doing actually an AI generalist engineer? Right? Coming back to the verifier's law, it is not easy all the time to actually verify what you have designed. Right? And that's where you have all these simulators, and you have to actually, sometimes some of the engineering designs might take a lot of computational effort to actually verify. And so disciplines where you can do a quick, low-cost verification are going to be the ones which are getting AI-fied, so to speak. Data, right? Barriers to data is always a key problem. While there is a lot of data available in public domain, high-end engineering will always relies on specialized data which is not accessible outside, or it is not even digitized. Right? It might be in the form of tribal knowledge of a few people who know exactly what needs to be done, right? But it's not really digitally captured. And finally, to build such models, right, it takes a lot of money and patience. And of course, that is a roadblock. I don't know whether in our country we can have such kinds of money and patience, but if you take some of these generalist models, it has taken a lot of money, and it has taken many years. Of course, now you can build the next version of the model much faster, but to get to this point, it took at least a decade. Right? And of course, the initial attempts will not be that. You'll say, what is this model is not doing that great? Even my son will do better. But I think we have seen how the hockey stick of AI, how it improves very rapidly. So if we could do this, what would it mean? Like, what is the promise of this, right? Suppose I had such an AI generalist engineer. So, I think doing Eng AI, right, that is going beyond Gen AI, for us, I think is going to be really important, because it will allow a sovereign Eng AI framework which will assist in rigorous and rapid and high quality engineering design. Right? Having access to such a tool will enable our industrial base. It will really lift up our industrial base. We'll get to Industry 5.0. Right? We have been in Industry 4.0, which is all about IoT, digital data, and so on. We'll get to Industry 5.0, where AI becomes like a first-class entity working with our human engineers in the industry. And it will make it globally competitive. And the cost will become very low, right? Because we'll have high-end engineering at commodity cost. And I believe that it will unlock our manufacturing potential, and it will enable rapid design and manufacturing of custom engineered products, right? Because if I have this super intelligent AI tool with me, I can do anything, right? And I believe that this will really unleash creativity and capacity amongst product designers, creative people. We can focus on creating things, right? Creating new products, innovations, And many times you have an idea for doing something, but you don't have the engineering skill or resources to do it, right? But now you have it, you will have this on your phone, which will tell you what and how to do it. So one of the, if you were to embark on this, there's always going to be a question, should I be specific to a domain? Should I make an AI specialist engineer, or should I make an AI generalist engineer, right? So we see that debate going on with AGI versus specialized intelligence, right? Artificial general intelligence versus specialized intelligence. And there are trade-offs to both. What this means is that the jagged edge of intelligence, right, the point which was raised by Jason, is that some engineering disciplines will be harder to AIfy, right? Like electrification, we have AIification which is happening. Some disciplines will be harder to AIfy, mainly because of inability to access the data which is needed for training, or inability to train the models. Right. So maybe it makes more sense to only focus on those disciplines where we have all the necessary conditions, right? So, show deep progress, for example, in protein design. Right. On the other hand, general intelligence can actually help sometimes to fill in for lack of data in certain specific areas. For example, if some of the techniques might transfer, your knowledge and skills might transfer from one domain to another. And in engineering, there are always certain common principles which transcend a specific discipline. Modularity, testability, composability, robustness, resilience, manufacturability, how efficient you are in utilizing resources, so on and so forth. And so these are things which kind of emerge, and hopefully the AI generalist engineer will learn this without anyone telling it to, and then these then get transferred, right? Leading to these kinds of emergent behaviors. And of course, I think as a practical matter, we'll probably have to have both approaches going forward, right? A generalist model and a specialized model. And again, it comes down to money and ability to take risks and bets. So what are the opportunities in this space? So I think I look at this as a very exciting time, and it's in the short to medium term, I think there is a huge opportunity to create and monetize AI-based technology platforms to transform engineering in specific verticals, right? You can take, for example, thermal design, right? Thermal design is such an important area, cutting across all engineering disciplines, from micro scales to mega scales, right? Can we have a thermal foundation model which will allow me to do thermal design, thermal analysis, right? And that is what one of our startup companies in ISC is focusing on, and has also got some money from the government for creating such a model. Again, in the short to medium term, skilling, right? And I'm going to talk a little bit more about it in the next few slides. Skilling, especially engineering skilling, I think we can really transform using AI technologies and tools. In the long term, I believe that once we have such generalist AI models for engineering, it will really unleash cross-disciplinary engineering capabilities. Suppose I want to do a custom prosthetic for a particular person, right? It involves a combination of bio, neuro, mechanical, electronics, software, right? At least 5 different disciplines. Having access to all that knowledge through a single source is going to become really important and feasible. also in the long term, everyone can do engineering, right? And we are seeing that in many other disciplines, especially software, and I'll give you the example of that. If you are a horticulturist and you want to design a greenhouse, you have to kind of figure out how to do the thermal design, right? As I said, where should you put your vents in your greenhouse so that you maintain the optimal temperature, right? You will have AI which will help you to do that. You focus on your horticultural work, and AI will help you design the rest, right? And this is where I see in the long term, it's something which will enable everyone to actually, do and design their own products in a much more efficient way. And what does it mean, right? So what is the implication of this? One is that I think we will be doing more with less. The negative of this is that, we are already seeing that in many industries as they're starting to lay off people, more work is being done with less humans and in less time. On the other hand, every human can do more, right? So that is the promise, if we are able to embrace it and actually adapt and use it. And I also believe that the silos which we have created, these discipline silos, right, they will become history. And barriers across discipline will be removed, and we are engineers. We are not just mechanical engineer or software engineer or electronics engineer. We should be able to engineer anything, right? And we will have the access to the specialized knowledge to help us do that. And of course, it has a huge implication on engineering education. What is it that we should teach our engineers, right? If an AI can do what I'm teaching right now to a student, what should I be teaching the student? And perhaps collegiate education, as you know it, is going to cease to exist, right? And this is not just my personal opinion. I think some other people in eminent positions have making this prediction, right? So I think it's going to be a huge deal, which we should, embrace and think about right now, right? Time to adapt is now. So I just, given that I'm short of time, I'm just going to rush through my own journey of using AI tools. I teach this course called Mathematical Techniques for Robotics and Autonomous Systems, mainly linear algebra and probability as applied to roboticists. As you know, learning really happens when you're doing things, right? When you solve problems, when you're working, and building things, right? As an engineer, you have to do that. And it's very difficult to do that 1:1 with every student in the class. And that's where AI has become really critical. And clearly our current system is woefully inadequate, right? We are training engineers within quotes, right? Training within quotes. So I asked myself, can I create an AI training teaching assistant which will really help me teach every student, right? And there are two lessons out here. One is engineering of such an AI assistant itself. Second is what the assistant does, right? And so just a high-level diagram of what this assistant looks like. So the student works with a Python notebook, solving problems, writing programs, and so on. And for every question, when they write an answer, they say check or help. It goes to a AI agent which I created, hosted on the web, which calls an LLM agent and gives feedback. And this is the system I built, and it's deployed, and my students are using it right now. Just to give an example, simple, find power of a matrix. That is a question, and then the answer, you write some answer, and then you say, yes, check my answer, right? And it will come back and give like a pretty detailed feedback. So this kind of feedback is very difficult for an instructor to give to every student, but AI can do it, right? And very detailed feedback and very interesting feedback, which unfortunately, firstly, you cannot read, and I'm running out of time to explain. You can also, a lot of coding questions, right? You can ask a student to write a program, and then the system comes back and actually tells, okay, your program is good, but you can do it better, right? You can make it more efficient and so on. And this is pretty amazing, actually. The technology has reached such a level that you can actually build these systems. And I think it's going to actually have a huge impact. And I believe that this is actually an inflection point in our history. And everything is going to change, and it's not just a hype, right? I do believe that everything is changing, and it will change. And so we have to wake up. Status quo with existing approach will become irrelevant. And many old jobs, those considered so-called intellectual jobs, are going to go away, right? And at the same time, I believe it's a huge opportunity for us, for especially the younger people. I think there'll be many new promising startups. and there'll be new unicorns which will emerge. And can we in India be at the forefront? Can we embrace it? Can we lead it, right? And be part of this revolution?
Thanks to INAE for inviting me for this talk here. It's a pleasure to join INAE programs anyway, and also a pleasure to visit IIT Kanpur. So I'll be talking about some of the research results in our lab, where we've been using artificial intelligence and not the really modern ones. I mean, modern ones we've just started now, but the 3 different works that we have done in the area of biology, where we were using computational methods, AI methods. And before that, before I go into what we've been doing, I will give a quick recap of the journey of AI from when it started in the 1950s, or maybe earlier, to where it stands now. We have already had a fantastic walk through the journey of AI in the plenary talk by Professor Parthopratim Chakraborty. So it'll be maybe some points maybe slightly repeated here. So as we all know, AI has had its ups and downs. It started somewhere in 1940s, 50s, and saw its 2 winters, and right now we are here. And the future, we don't know what the future holds. There are some people who think that it's going to grow, become unmanageable and very scary. It's going to be everywhere, and we may become redundant. Another where the excitement will fade, and there will be certain applications which will benefit hugely. And the next AI winter is around the corner. So there are different thoughts about where AI will go in the years to come, but as of now, we don't know. What 50 years later, what human beings will be doing is something we cannot predict now. So it started way back in 1940s. Alan Turing was already thinking about thinking machines. And the first model of neuron came up around 1943, McCullough and Pitt. And the Turing test was designed in 1950, which was a test of whether whether a machine is intelligent or not. And it goes something like this, the Turing test. We have an interrogator and a computer and a human, but the interrogator cannot see the computer or the human. And there's interrogator engages in a 5-minute keyboard conversation. Either the computer or the human will respond. So if the interrogator is unable to reliably distinguish between the human and the computer, that is who responded, then the computer would be termed as it has acquired intelligence. And it has been really tough to pass the Turing test. In fact, in 2014, one chatbot, a computer program, fooled the 33% of the judges into believing that it was a 14-year-old boy who was responding. But officially, Turing test got passed only very recently, in 2025. We'll come to that quickly. So then the development continued, the checkers playing program, and in 1956, the term AI got coined. In 1958, the term machine learning got coined, and Rosenblatt developed the perceptron, which is the basis of artificial neural networks, which is very simple model, a nonlinear function here. It was originally a linear function. You just have certain inputs and the weights on these inputs, and you have a bias term, and there is an output which is coming out, and usually it actually is modeling a hyperplane like this. And the parameters here that we have to learn, these are the W's. The W's are what we have to learn, and the bias, and this is the input. So we know the input, we know the output, and we have to learn what are the W's and the B's so as to model this relationship between X and Y. So that was very nice. There was steepest decent method for learning those parameters. Everything was going very nice. The development was continuing. Then NLP became important, language models, and also the first expert system, Dendral, was developed. And then in 1969, the first IJCAI was held, International Joint Conference on AI, and Minsky and Papert published this book, Perceptrons, An Introduction to Computational Geometry, but there it actually brought about the first AI winter. It went down. After this, it went down because the failure of single-layer perceptrons was demonstrated. It could not solve the very simple XOR problem, okay? And because at that time, although multi-layered perceptrons, not single-layer, but multi-layered perceptrons, that multi-layered perceptrons could solve the XOR problem was known, but the training algorithm was not yet to be discovered. So, and there were many other reasons why this AI research hit a winter. But that was it. The machine translation hype was also busted. In fact, there was there's this famous thing which the spirit is willing, but the flesh is weak. Translated into Russian and translated back into English, came out to be the vodka is good, but the meat is rotten. So, I mean, these things sort of made people realize that AI is not delivering on its promise, and it was the start of the first AI winter. But then, of course, Rumelhat, Hinton, Williams, they brought about this very, very important paper, 1986, the Learning Representations by Backpropagating Errors. And CNNs started appearing, the convolutional neural networks. So it re-emerged. But then again, because of very high promises, the hype, failure of expert systems and high costs of certain machines, the Lisp machines, it brought about the second AI winter in late 1980s, which, of course, in about late 1990s, again, there was a re-emergence. And we know of this very important thing which happened, IBM's Deep Blue, which in a pair of 6 game matches, in the first match of 6 games, in 1996 in Philadelphia, Kasparov won 4-2. But this already showed that at least in 2 games, Deep Blue had won. So the chess grandmaster was defeated in 2 games, but overall the match was won by Kasparov. But a repeat match of 6 games, there Kasparov lost 3.5 to 2.5 to Deep Blue. So this actually gave rise to this a documentary also, Game Over, Kasparov and the Machine. Then, of course, the development continued. 2009, we have this, the GPUs were available for training large neural networks. 2012, the AlexNet came in, interest in deep learning in all-time high with CNN by these people. 2013, DeepMind introduced deep reinforcement learning. 2014, GAN came in. GAN was generative adversarial networks. So 2 networks trying to compete with each other, one network trying to fool the other, and in that way, the learning was happening. So this was all very, very fast developments happened. 2016, DeepMind's AlphaGo defeated the top Go player, and then diffusion model came in 2017, which was a way to reverse engineer the process of adding noise to a final image. And very, very importantly, Google researchers developed this concept of transformers, which is attention is all you need. So it was here. This brought about the remarkable change and became the foundation, became the basis for the large language models, okay? And then, of course, the development continued. 2018, we have the GPT releases from 2000, and the latest one, GPT-5, I think, August 7th, 2025. And of course, we know that Bengio, Hinton, and LeCun, they won the Turing Award in 2018. 2021, AI released DALL-E, which could generate images from text prompts. So the authority of humans was challenged now. The creativity of humans was challenged. And as I said, this should be read as 2025. ChatGPT 4.4, that was when the Turing test actually got passed in a UC San Diego study. It was conducted by these researchers. The participants held simultaneous 5-minute text conversations with a human and a Gen AI model, and it was very difficult to distinguish. 73% of the time, GPT 4.5 was judged to be a human. So significantly more than any other, in fact, any other competing models as well. So, and now we stand where we are, with most of us very confused, those who supervise research students. We are struggling also to get the students into areas of research. What to do next is a major question that I think all of us are faced with. And for everything and anything, we have this tendency of going to ChatGPT. So I also had this, and I just gave it a question that how to give an interesting keynote talk. It gave me a very nice list of points and wrapped it up with additional tips. Okay, and there you can see dress appropriately and use humor wisely. So very, very appropriate tips for a good talk. So anyhow, but why did it move in spurts? Why was it not a very smooth journey? Because at every point, the theory was there, but the technology had not yet caught up. Storage was expensive, speed was less. As soon as these were addressed, the AI flourish happened. Okay, so now it looks like the big companies are holding the foundation models. We'll be doing small language training now with our own data sets. So now the power will be with whoever holds the data. That's where looks like things are going. So holding on to data, generating data will be extremely important, at least for the near future. So just to put things in proper perspective, AI, within that a part is machine learning, and within that we have the deep learning, which is essentially different forms of neural networks. And we know that AI is everywhere. I will be focusing on the next 10 minutes. I'll just walk you through some of the applications that we have done of AI in healthcare, AI and machine learning in healthcare. Again, there are many different areas in healthcare where we apply artificial intelligence and machine learning methods. I will just focus, but before I go into that, just to put again very quickly things in proper perspective, because this is the basic, the central dogma of molecular biology is the basis of whatever biology would want to do. And all the data sets most of the data sets in molecular biology is around this particular set of processes. So we have the genes, which are pieces of DNA. From there we produce, the cell produces something called messenger RNAs, and from messenger RNA through another step of translation, we get the proteins, and proteins are like everywhere. So you can see these are sequences. DNA is a sequence of 4 characters, A, T, C, G. RNA is a sequence of, again, 4 characters, but A, U, C, G. And proteins are actually sequences of 20 standard amino acids. Okay? And as soon as we know this, we are already looking at data. And there are various types of data that we look at. One, of course, the sequences, the DNA sequences, RNA sequences, protein sequences, the structures, because these are all 3-dimensional molecules. They will take up certain structures in space. So the nucleic acids, they have structures, proteins and drugs. There are different types of structures in biology. Expression data, what is expression? Expression is, if we go back just one slide, expression essentially measures how much of the messenger RNA is produced from a gene. Okay? So if the gene expresses highly, means a lot of mRNA is getting produced, which would translate into a lot of protein getting produced. So gene expression measures how much a gene expresses itself through the production of messenger RNA. And there are a lot of networks which are in action inside the cell. The gene regulatory network, protein-protein interaction networks, drug-drug interaction networks, and all of these actually demand sophisticated algorithms for solving that. And that is where my work has primarily focused, on developing algorithms for solving biological problems by analyzing biological data. And of course, the images, different types of images and electronic health records. These are also amenable to huge amount of analytics. So I will be talking a little bit about gene expression data. So as I said, gene expression just measures how much of the messenger RNA is produced. And that varies over time. It varies over different conditions the cell is in. It varies over different individuals also. So these are often considered as time series data, etc. So what earlier, the technology which was available was able to only measure, the gene expression data, expression of genes averaged over many cells. So it was an average expression that one could measure. But latest technology has become available where it is possible to measure the expression of individual genes in individual cells, okay? So if you think of it, you have many cells, let's say 100,000 cells on your rows, and you have all the genes, about 30,000 genes on the columns, and this matrix will give you the expression of a particular gene in a particular cell. That technology is available, but with that technology, the challenges which are coming is, this is called single cell RNA-seq data. That's the expression data. It is a matrix where suppose you want to cluster, but the characteristics are, it has substantial amount of noise. And as you can understand, it is a large data set in very high dimensional space. So how do you develop your algorithms? The standard clustering algorithms will not work here. So what do? We have come up with a method of clustering single cell RNA-seq data. And this is called dropclust, which has a version 2.0 as well. But essentially what we were doing is, we have to sample because we cannot work with 30,000 dimensionals in a 30,000 dimensional space. So we are sampling, but we used a method whereby the structure of the clusters, so even small clusters, because in sampling what happens is, if there are small clusters, meaning they are rare cell types which are seen only a few cells of that type are there, then if we are sampling, very likely we will lose that cluster, but we don't want to lose it. So we came up with something called structure preserving sampling, and where in this we were using something called locality sensitive hashing. Right? And locality sensitive hashing, it's hashing, as we all know, is where you want to spread out the data so that once you give the key, you can immediately retrieve the data. Right? So what in normal hashing we would like to do is to avoid collisions so that data points don't collide and go to the same location. In locality sensitive hashing, we actually want data points to collide if the points are close to each other. So that is what locality sensitive hashing is about. And we use that for structure preserving sampling. And we did a little bit of innovation in principal component analysis as well. It was the standard principal component analysis, but then which principal components we will pick up is something that we brought in a little bit of change there. And then we actually did the standard pipeline. So nothing much there, hierarchical clustering, etc. But just one quick result on peripheral blood mononuclear cells. These are actually immune cells in the blood. And you can see here, I've marked certain small regions. Those clusters were also detected once we used dropclust. So the interesting thing was that this CD52 regulatory T cells, which comprised about 0.5% of the total population of 68,000 cells, those were also detected. And it's not that this is a new cell type. CD52 is known, but what was interesting is that in this data, in this particular data set, it was not known that CD52 existed. So that gave additional biological insight into the data. And those are things which become interesting in the long run. So with that, let me quickly go into another problem that we've solved. How much time do I have? About 3-4 minutes more? 5 minutes, okay, yeah, I'll do it fast. So on a problem in drug design, so remember when we were doing this work, it's all pre-LLM era, okay? So you will not find LLM or deep learning here, pre-deep learning era. So drug design is a very difficult problem, and that's why the drugs are so expensive. Companies typically take about 10 to 15 years for a drug to come into the market and costs huge amount of money. The research costs huge amount of money for the company to identify a workable drug. There are many small molecules that they start off with, but then one by one they fail, and then only maybe one or two they can hit, which goes into the market as a drug. So now what is tried is something called rational drug design, where you actually use certain principles in order to do the computational stuff, and it is now almost expected that drugs in future will be designed on will be totally designed on computers. Traditionally, drugs were discovered, by chance, observation of nature, etc. What works, what doesn't work. I will skip these parts, but it just shows that there are proteins. Suppose a pathogen has infected. This is a flu virus. If a flu virus infects, this is a flu virus which is shown here. There are proteins on the virus, and there are proteins on the human lung cell, for example, which interact with each other, and that pushes the virus inside the human cell, and then certain proteins swing into action, proteins of the body, proteins of the virus, and then this virus makes multiple copies of itself, and then the human lung cell bursts, and these viruses have multiplied so many times, and now they are free to go and infect other cells. So that is how a pathogen typically works. And rational drug design principles have been used to actually design molecules which are in the market. So what we were doing is, we were taking an a multi-objective optimization approach for drug design, and there were several objectives that we could identify. So, and we used a multi-objective optimization, as I said, where essentially in a single objective optimization problem, what you do is you take one solution and try to improve it. In multi-objective optimization, essentially what you do is you have a surface, a set of trade-off solutions, and you try to improve that surface. Because you are not, remember, you are not converting a multi-objective optimization problem into a single objective one. Suppose you had 3 objectives, you could have done a weighted averaging, W1 F1 plus W2 F2 plus W3 F3. Here we are not doing that. The objectives are kept separate, and they are simultaneously optimized, and the objectives are such that they conflict with each other. If you improve one, the other becomes bad. So how do you tackle such problems? So this is multi-objective optimization problem, and we were using a genetic algorithm-based approach as well as a simulated annealing-based approach. These are all optimization techniques. They are meta-heuristics. And we were using several functions that we wanted to optimize simultaneously. And as target, we took a protein of the bacterium, of Mycobacterium tuberculosis, the one that causes TB. Okay? And this protein actually is a protein which does DNA repair. So once we have the virus, the bacteria has infected the human being, and the person takes antibiotics, the antibiotics goes and damages the bacterial DNA. Okay? And this protein, which the bacteria brings along with it, it will repair that DNA. Now, if you are able to stop this particular protein from repairing the DNA, then hopefully the disease can be arrested with antibiotics. So this is the purpose why RECA protein is often taken as a target of Mycobacterium tuberculosis. So what we did was, we looked at this protein and we tried to design small molecules from scratch which could work here. And our results showed that several molecules were generated which are already known to be inhibitors of RECA protein. Okay, these are known. There's nothing new here. But the algorithm generated on its own. That gave us a bit of confidence on the method. So along with these known inhibitors, some new inhibitors were also generated. And these are the interesting ones. We did some further studies with these molecules which were generated. And some of these proved to be quite interesting, because there were other studies like QSAR studies which one can do to figure out if these molecules are really good given that particular target. Okay, so this is another work that I just wanted to quickly walk you through. And the last one that I will just tell in about 2 minutes is something to do with graph neural networks. As we know, graph neural networks are a relatively recent development where a graph is actually embedded. There's a representation of this graph which is learned. The representation embedding is in such a way so that two nodes, if they are close to each other in that embedding space, they will also be similar. The embeddings will be similar to each other. So that's how the embeddings, the representation of the graph is learned. Okay? So what we are doing now is we are applying graph neural network approaches for analyzing networks of drugs and proteins in order to predict adverse events, so side effects, adverse side effects that might happen. And here we are looking at this graph where, as you can see here, the triangles are the drugs, okay? The triangles are the drugs, and you can see some circles here. These circles are the proteins. So drugs are interacting with each other. They are known to interact with each other. So if this drug and this drug is given together, then R2 is the side effect which is observed. So that part is known, but not every such side effect is known. Every such combination has not been tested out. So whatever is known is put in this graph, and also these are the proteins, and every drug essentially targets one or the other protein. So those linkages are also created here, as well as proteins interact with each other. So you can see here, it's quite a complicated heterogeneous graph. And we are using graph neural networks to predict side effects of drugs in combination by analyzing this entire network. Okay, so task is to assign a new medicine to a person considering other diseases that the person has and the ongoing medications that the person is on. So this is a project that we have with French collaborators. So it's an Indo-French project, which is currently is just getting wrapped up. So with that, I think I will stop my whatever I had to just tell about the things that we've been doing in our lab. But these are some recommendations where I would like to actually tell that we have to take a problem-solving approach. I mean, if several groups can sit together, in my own institution, I'm trying to build such a group which will first not think of methods, but let's think of a problem that we want to solve and then see what is necessary to solve that problem. It should be a very big problem that we want to solve, a problem that faces the country here. So, and a major focus has to be, of course, on development of Indian data sets, because in every domain almost, even in computational biology, whatever methods we develop, we finally end up applying it to data from the US, from Europe, or even from China. But Indian data sets has been difficult to find, but that is changing. Now, a lot of Indian data sets are getting built. So you can see DBT, ICMR, CSIR, a lot of efforts are now on, but pace is still low, and the quality of the data is not very high as of now. And other recommendations, of course, we have to have a national level EHR data. So it's like an Aadhaar card, if we can have my entire medical history is over there, that would be really an ideal way of going about doing this. And personalized medicine, we hear of personalized medicine so much these days because every individual indeed is genetically different. So medicines also should be personalized. But for a country like India, where our target should be, if I just go back here, power of AI to be harnessed to provide access to high quality. Quality has to be high. Quality cannot be compromised. Scalable, affordable healthcare to all. If that is the target, then too much of personalization may be very expensive. So if we can have not personalization at the individual level, but at a group level, at a cluster level, at a community level, if personalization can happen. And we also have to reevaluate and calibrate the global standards that we go by. Okay, maybe we are misdiagnosing or over-diagnosing or under-diagnosing our conditions. So our standards have to take care of the genetic makeup of Indians. So we need to probably relook, reevaluate, and recalibrate these thresholds. So with that, there are, of course, some other concerns here. And this also, I will say, tendency to fit all problems to the LLM solution. This is something I think we need to reconsider. So with that, thank you very much for your time.
Thank you to INAE for inviting me and giving me this opportunity to address this August gathering, and to IIT Kanpur for their excellent hosting. So you saw the biodata, which I can't change because it's a historical fact. But as far as the talk is concerned, nothing much of defense is going to come into it, and never mind all those acronyms. But it is a fact that starting from my days in Caltech graduate school till I was in CARE, AI one way or the other, whether I liked it or not, was always part of either what I had to do or I had to guide somebody else to do or defend what somebody else has done. So based on this, there were many things which I had never had a chance to talk about, which I thought that this would be an excellent opportunity, and the way the invite came, it was about giving policy inputs. So I de-emphasized the hardcore technology part, but I'm here till day after, so anybody wants to ask about the underlying details, I'll be happy to do so. So as the title goes, there is a question of industry synergy, and then there is this concept of the design and the certification. So I'm showing on the left-hand side what is the usual flow. Now, when we talk about design, so let's say from anywhere between 1830 to 1980, that's 150 glorious years of post-industrial revolution engineering, and certain norms, behaviors, expectations got crystallized and understood by everybody. And in that paradigm, you would start with requirements where people would talk in terms of their functional requirements or environmental requirements, whatever, based on which the engineer, I'm sorry, that particular color is not working out too well. That's the design and development part, that yellow box. So the engineering teams would then do the design and development, which would undergo all kinds of reviews, validations, preliminary reviews, detailed reviews, critical design. Then you would have quote-unquote metal cutting, so on and so forth. Now, after that, there would be the acceptance test, initially in-house, then maybe a quality group or IVNV, and then finally the customer would be doing it. And typically for those items for which the customer would not be able to look under the hood and appreciate certain critical parts, it would always go for a technical certification by a competent authority. So whether it was fire safety or flight safety or crypto safety for military, this certification was always there. And similarly for food safety or drug safety for anything that we are consuming. And then you had the production and the costing part. So this paradigm was well understood. Everybody expected anything with engineering to follow this. And things were going fine, and people have said before me, it is settled, it is understood, and I would say mastered. Mastered simply because it was going slowly enough that you had 2-3 generations with human beings for every generation of technology, so they were really mastered in those days. The first jolt, in my judgment, came in the 1980s when we suddenly started getting into software engineering. Now, if you see the very name of the department, computer science and engineering, so clearly people could not make up their minds whether it was in science or engineering and put both, missing elements of both. Now, what that meant is that we had a large amount of expectations from software. So the software-defined world was hyped way back. And then you had IEEE Spectrum telling us that 80% of software projects are failing. And there was a lot of hue and cry. People lost their jobs. People lost their reputation. Eventually, after muddling through, we came to this software engineering in a more rigorous sense. We understood details and entropy, and so the stack became heavier. We had equivalence classes understood, and so we had analysis classes, design classes, the entire object-oriented programming took off. So some things happened. But it happened not because we understood what we were doing, but because we kept failing and trying something or the other. In the bargain, going from classical engineering to software engineering and making that solid took a good 30 years. And it was 30 years of pain, and in many cases that pain has not completely gone away. Okay. Now we are coming to AI. And AI is as different from simple software as software was from hardware. Now the question and the reason for my talk is, do I want another 30 years before the bleeding stops? And I think we can do better than that. Of course, we are not God sent to be able to get it right in the first shot, but at least if we intend to understand the difference of the underlying paradigm and say, therefore, what changes we need to make with respect to so-called requirement gathering and the design system and the development system, it should be better. Now, there is, of course, a lot of hype on AI going on. But if you think about it, all of it is about, here is an AI product, isn't it wonderful, don't you want to use it? It is not being custom developed for you with any kind of an assurance or a guarantee. chances are in order to install it, you'll have to say, I promise not to sue anybody for anything, and hit that OK button before it will even work on your system. So that's not the way engineering went. You don't sell a house saying, okay, if you want to buy it, but if it comes down on your head, I'm not responsible. You don't say that with respect to food products and medicines either, because we have a way of getting assurance. Now, when it came to software, the utility was so high and the assurance was so low. The big people managed to get away by making people click that OK button. That's not really a satisfactory state of affairs. It will be more unsatisfactory if that same practice continues into AI. So what happened? With respect to the software, the adaptation to software was we had this software engineering after, say, the 90s, and then all the CMI and all those Carnegie Mellon kicked in. And incidentally, why did they get hired? DOD was forced to give them that task because otherwise they were bleeding money. Everybody was promising DOD the cat's whiskers in software systems, and then it was going and failing. So should the same thing have to repeat from scratch for AI? Probably not. So this needs to be done proactively, and let's look at the synergy between the stakeholders. There's end users, designers, producers, operators, regulators, of which the designer part of it is a tech crowd. That's where all the geeks are, whether it is the graduate student or whether it is a fresh hiree or it is the tech lead or the project lead in a project. So that part of the conversation is within technologists, and you can say this is my language today and that is my jargon tomorrow, no problem. But at the point of the requirements, you are talking to a lay user who's potentially not a techno geek. And at the end of it, you're talking to society at large, where again, the gobbledygook of languages and technical terms cannot possibly be what the rest of the society is looking from a engineering community. So these are the 2 points which I have chosen to highlight, that this part definitely needs fixing. The rest of it is our internal problem as engineers, that we keep changing a language every 5 years and we keep changing the best model every 3 years. That's our internal problem. So now getting into some of the details. See, when it comes to the requirements, and just to make the transition into AI more gradual, I've started from the systems, gone to the software, then gone to AI. Now, as far as the role of requirements in engineering is concerned, that's kind of canonical. A, communicate user expectations. That's the most obvious part. But then there are a couple of things which are also there. 2, you want the management to look at it and make an assessment with respect to the scope, complexity, effort, and risk. Every time a user says, I want something, every company doesn't get up and bid for it. Okay? And in any case, you have to give estimates with respect to time, cost, reliability, availability, so on and so forth. So the requirement should allow that second function also to happen. Thirdly, when you are giving the requirement and you say yes, after that work starts in what sense? You are supposed to start doing designing, prototyping, development, so on and so forth. So if the requirements is not enough to enable those processes to happen, you'll be going back again saying, okay, now that you have asked for it and I have bid for it and won, now let us really say what the project is all about. How dangerous is that? You have signed a legal document, somebody has got an expectation set, and now you're trying to find out what the project is all about. And yet that has happened. It has happened in software in the past, it is happening for AI today. So in the case of physical systems, this did not happen. Why? Because you had, first of all, linear space-time invariant systems. That itself simplified a lot of things. Secondly, there were physical systems based on laws of physics you understood. And that linearity would typically, and this is most thinking of the electrical and the signal processing crowd, that because of that you had an eigenbasis, the Fourier harmonics, you figured out what to do for the Fourier harmonics, the rest of it could be sorted out. So there was a very underlying regularity in the universe which allowed us to do these things so easily. And the physics was common. It was common for the person giving the requirement, it was common for the engineer designing it. And I think that point was mentioned today, that yes, there's a lot of underlying physics, and yes, that's great for the classical part of engineering. When it came to the software systems, now you had a very nonlinear information processing system. If you are trying to make decision based on comparison between numbers, some Boolean variable here and there, a little bit of a change can lead to a catastrophic difference in the output. It is not the case that if I built it for 30 tons, then probably a 31-ton truck is not going to break my bridge. True, it won't. But you can't have any such assumptions with respect to a software system. So they are far more required to be right in the minutest detail. And you don't expect this epsilon delta behavior to save you. Secondly, you have to therefore not just say in terms of, okay, I want to shine a light and see how far it shines, or I want to send a radio signal and see how much, whether I get 1 Gbps on my channel on a good day or not. Now, if it comes to the software systems, it is not that physics. So you're defining an equivalence class. If that person is making a deposit, ask these questions, perform these actions. If that person is asking for a balance inquiry, get this information, take these actions. So again, if I say I want 100 rupees as opposed to as I want 200 rupees, do you expect a completely different subroutine to kick in? No. So you define, so that part of it is not different. So there it is just a matter of the number being slightly different. So you have a very big input space. You break it into a few equivalence classes and say that for each equivalence class, I'll have a response method implemented. And that was what Grady Booch and the rest of them were doing with respect to UML. And it was after that that a lot of the fighting stopped in the requirements part of software engineering. And finally, therefore, you came to this equivalence classes, and subsequently, based on that, the designers would come up with this use case objects and classes, and actually the analysis classes you discuss with the users first to make sure you are on the right track, then you get back and do something else. And the worlds were very different. So now that engineer, the software engineer working on telecom is not a telecom engineer necessarily. So therefore that gap in understanding was always bigger. But with all of this it worked, but no space, no basis, no physics, no epsilon delta, which we ignored to begin with. So we assumed software will work much easier. After all, there's no metal cutting, so the biggest risk in engineering has been taken away. What is left? Hit that brown exclamation mark and the code will compile itself. It didn't. And every time the big boss came and made a last minute suggestion, however innocuous it was, it always led to a long-term crisis later on because of the nonlinearity. Now, all of this we did the hard way in going from hardware to software. Now we come to AI, and I'm taking a more detailed look here. So you had three things: expectations, assessment, as well as enabling inputs. Now, let us look at how this AI thing started getting used first, and it's not getting used only today. People have been promising it and been trying to use it much earlier, 20 years almost. So the initial inputs would be textual, because after all, your SRS for the software was a piece of text. So why not do it even if it is AI into it? So they would give things like, okay, I want bridges and railway stations and airports to be understood in that image. That's a textual description, but it doesn't allow anything to happen. It doesn't even say who took the pictures, when they took the pictures, and how close the various classes are. Similarly, when it comes to giving illustrative examples, after a lot of blood and tears, then people understood, okay, AI needs data. That nickel fell. So now it started coming with 10 pictures of airports, 5 pictures of ports, 3 pictures of a railway station. Now you go and analyze everything based on that. Again, it didn't work. It is better than just the textual description. At least you can guess what kind of images they are looking at, sensors they are having, but not otherwise. Then eventually, so eventually, this is what it is coming to. It's looking for a bigger, much bigger set. So what is design? In the classical era, there was something. In the software design, there was something. Now, in the case of AI, what does it even mean to do the design? So you would have to do a model selection. You have to do a parameter estimation on that. Then you would need iterative refinements for improvements, because the specific data relevant to different users would be different. And finally, this entire thing is driven by a curated data set. So what is meant by data adequate for AI design? So these are some of the things that has to be checked off if you want to say that as a person asking for a bespoke tailor-made AI solution, This is the kind of things you have to get into before you say that the data is enough to drive an engineering design process. The iconic things has to be defined, the boundary values have to be defined, and typically you have to allow for a failure of both, because no user today, in spite of the few years of digitization we have had, will have enough data to necessarily do it right. So the mitigation for what happens if I don't have every class or every class boundary representation will also have to come in. Now, that's one part of it. Next comes when you're trying to deliver it. And this is assuming that you took it as an order and you're trying to fulfill an order. If you want to deliver it, what happened so far was this, the typical engineering thing where everything was designed up front, everybody signed off on it, and finally you just bought a piece of equipment and you plugged it in and your television worked or your computer worked. With respect to AI, much of the work remains to be done after you have taken the delivery. So therefore, after you do the design, the designer is only doing this much, which is why it actually looks like a no ops to be doing a design review just after the project has been sanctioned on an AI project. Then the user has to go in and fit in this actual data and see the performance of the AI system against the human operator, because the human is lambda equal to 1 for AI. It is not 100% performance. And with respect to this, you will then see whether it actually worked or not. And different people have different data. And finally, the user operations will proceed. So if you want to do it, there is a is this the PPT or the PDF? Oh. Anyway, okay. So actually, if anybody asks for it, give them the PDF. PPT is not coming correct. So in the traditional sense, what we were doing is we were dealing with a lot of the risk up front at the design stage. But once you delivered it, it had to just work. But it would work for a specific static environment model. That this is the person, this is the kind of data, and it will work. AI gives you a flexibility. It is putting the risk towards the end of your delivery process, but now you can tailor-make your AI solution differently for different customers. And even the same customer can keep making the solution adapt itself to a change in environment, which the traditional solutions never had. But this conversation has to be explicit. If you did not have customer adaptation and if you did not have post-deployment adaptation to be done, only reason for AI would be to use AI in the design process, as was being talked about, that can I use AI to do better engineering. That usage is independent of anything else. But if you want the AI to be AI in the hands of the user, not just helping the engineering in the design, then you have to be very clear that that risk mitigation is not coming for free. The risk mitigation with respect to customization and adaptation is coming at the cost of variable performance post-deployment. So one thing that has always cropped up is how do you do an ATP on an AI system? Because you cannot now say, I will only use that data which I gave at the beginning, because then you could fake it with a lookup table, and no self-respecting AI person wants to deliver a lookup table. So of course the data will be different. At the same time, if the data has a foundationally different PDF, then of course any AI you have built on the previous data is going to fail on this data. And the best of AI doesn't always score 100%. You don't have to get 100% to publish a paper. In fact, people will say you have overfit your data if you have published anything with more than 95, right? So that being the case, how do you deal with this business of passing an ATP? Those of you who are in college, fine. But if you ever try to run a startup and deliver to the government, you will face this problem. And then you will not get your payment. So there are methods for actually doing this. And we explicitly came up with something called a calibration data, where you say that among other things, and this is an intermediate step, you would have to say here is a set of inputs on which the system is supposed to give the following set of outputs. That may not be 100%, but it will be there. Why do we need this? The second problem with AI is the number of runtime libraries that the solutions are linking are absolutely huge. So as a result, these days we find that whenever we give anything to anybody else to deliver an AI solution back, they are not just giving that solution.exe. They'll give a virtual machine with everything contained to say, in this it will work. Because now you go and add somebody else's GCC or somebody else's JPEG or video graphics, then the whole thing is gone. So it's actually working in the Hanuman mode, that for the Sanjeevani, I bring the whole mountain back and hope that nobody will point a finger at me. So if it is that sensitive, you have to also realize in real life, the solution can drift for reasons of environment drift, computing environment drift, not even the parameter learning drift. So for all those reasons, a calibration set should always be provided with an AI so that a user can always check whether a IT environment drift has hit it or something else has hit it. And then we come to this business of a human trusting an AI. As was brought out, this believability for these deep models is a lost cause. Why is it? Believability requires a conversation. Conversation means you and I should be using the same language, same vocabulary, maybe even the same textbooks. Where we are treating AI these days as black box learning, we are not teaching it a language or vocabulary, anything. It is learning what it can. It happens to be getting good results, so we pass it. That being the case, even a computer science professor and graduate student will be hard-pressed to understand a core dump from an AI. But we humans are still using experts in our own world. I don't have to understand my heart specialist to take that advice seriously. So what is it that we are doing? So we introspected, and what it came down to was these things. As human beings, we are seeing for reasons to believe an expert. Is there proof of familiarity? Are they an expert in that problem? Or is my dentist giving me real estate advice? Then forget it. Secondly, competence. Have they shown good performance on similar cases? And this can actually be numerically bolted into the solutions, and we have actually worked it out. And it is also amenable to vendor neutrality and black box. See, India is not only going to be using Atmanirbhar AI, much as we would want that to happen, but in the meantime, there will be AI coming from other people. How on earth are you going to say it is error-free, malevolence-free, or not programmed for something very specific? You can get through the details. The idea is that given an input, I can always see what is its distance to some n nearest inputs in the training set. Now, one thing to keep in mind, in AI, when we are capturing these features, there is an alignment problem. We are in a position to have a camera and take a picture, but everything that the user wanted about the person is not in the picture. So, when you define a user-defined class and you extract features from a signal, it's very unlikely it will be a unimodal distribution. If you hand label the data, you will still find multimodal distributions. So given multimodal distributions, when it comes to saying that something is familiar or not, it has to be that there are certain features which are similar to what you have seen before. Now, you can test two things. If the data point is very different from anything that was used in the training set, you can say this AI was not familiar with this, let's not trust its verdict. But further, that's not enough. AI is never uniform in its performance across its entire training set. So there are some parts it gets very good, some parts it makes significant errors. We need to be able to figure out whether the test probe is hitting that error-prone region or the down-cold region. So that's the proof of competence, and there is a numerical method for doing it. If we do these two, then given any OEM implementation, they can give us this calibration set based on which we can implement our own familiarity metrics. And the customer can actually do their own implementation. So I have bought something from some company, but I want to know under Indian conditions what is going to happen. The Indian patterns of TBs and COVIDs and things like that could have been very different from the Germans. So we would have to, even if we decided to take a classifier from them, to trust it in India, we would have to have our doctors with our images building our calibration and believability sets. Then we could safely use it. And lastly, so this is all about the details of how you can do both the calibration, the believability, and once you have these two, you automatically get the disclosure and the certification. This is about as deep as an AI certification can get. Going down and doing code line checking the way we do in aerospace has zero chance here. I mean, you'll be going and hitting 1 billion floating point numbers, end of story. So you have to see its actual performance on calibration data set. And if we do this, we we will get industrial strength and maybe even military grade assurance with respect to AIs. And this is the last slide I want to leave you on, that there tends to be a admission of guilt by engineers that, okay, we could have done this, it went wrong, or this is going wrong, that is going wrong. I have always felt that actually the complexity of the problems that we have been taking on have been getting worse over the decades. So initially the ones we were taking on in the classical engineering, typically they were known targets. We knew what we had to build and we knew how we had to build it. And so therefore there's what PMBOK would call the type 1 project management would work for it. It's just a matter of scheduling and making sure you've done your planning correctly. But when it came to software, people were not actually sure of what they wanted. They wanted certain functions, but once you built it, they said, no, not this way, I want it that way. So the form kept changing, even though for each of those asks, the method of coding it was never in doubt. Finally, when it comes to AI, both of them are in doubt. The person, once they see an AI in action, will start demanding more or demanding less. But even then, if a bank manager says, look at the client and tell me whether they will default on the loan, there's no business process automation that you can implement at that point, which is what the software engineers were doing. So now there is a brilliant and a crack that you have to figure out. Maybe based on the data you will discover it, or however you will do it. So these are the type 3 and the type 4 kind of problems. And if you actually read project management, the type 1 project is to project management what linear systems is to engineering. Great idealization, great for the textbooks. You can wax eloquent on eigenvectors and Fourier harmonics, but it is not the real world. So if we are doing type 2, type 3 and godforsaken type 4 projects, we cannot get browbeaten into using type 1 project management as metrics for the success of that project. And that is something all of you will have to keep in mind. Why? 1 lakh crore RDI funding coming your way. So good luck with that. Thank you.
Session 3 on drone technology. Our session chair is Professor G.M. Kamath, who is the Professor and Head of the Department of Aerospace Engineering here at IIT Kanpur. Professor G.M. Kamath is a Professor and Head Aerospace Engineering at IIT Kanpur. He was Professor in charge of IIT Kanpur Research Park between 2021 and 2023, and currently is a member of its Board of Directors. Prior to joining IIT Kanpur, he served in various capacities in CSIR National Aerospace Laboratories, Tata Advanced Materials Limited, Tata Consultancy Services, and Bombardier Aerospace, India. He obtained his degrees in aerospace engineering from IIT Madras and University of Maryland College Park. His research interests include aircraft structural health monitoring, corrosion sensing, monitoring in aircraft, and corrosion fatigue of aerospace materials. With that, I welcome Professor G.M. Kamath to chair this session on drone technology.
So good afternoon, everyone, and welcome to this session. Good evening, students, younger minds, renowned faculty members, and industry experts. Professor Nishchal Verma is one of my very good friend. I left academics and all this presentation 3.5 years back. But he gave me a call, said, Professor Ghosh, can you send some 3 names from industry? I sent him 3 names. Then why? Some INAE conclave is there. And where it is? In Kanpur. It's Kanpur and you are not calling me? But no, I'll call you, right? And then he is a smart guy, because why I took name of Professor Nishchal Verma, 4 or 5 years back, maybe more than that, I have been telling him, your deep learning execution talent is so needed, right? Especially when we have a limitation on EOIR, remember, because mostly on the startups, where is the money? And you can, if you can add a value to it in terms of DRI, detection or recognition or identification, whatever it is, right? I was annoyed that he didn't really start working on this. So he asked me, what is your topic? I said, drone technology, you and me. Now, once I have given that topic, I found formal mail came. Now I have to fulfill the content. Okay. And please understand, I approached all my younger students who are startup, Aurora Integrated Systems, CG Space. I just messaged them. If the title is drone, you and me, what is your interpretation? One girl, Tanvi Prakash from L&T also, she worked with me. She told, sir, me is the requirement and you is the solution. And how do you get a solution? I thought I am smarter. I said, are you hinting at innovation? And she told me, sir, there's nothing like innovation. Please use incremental innovation. And she taught me that engineering always stay at a survival mode. Engineering will always be at a survival mode. You remember the design starts from safety factor, then system has fail-safe. If there is no survival mode, engineering will not prosper. It will just die. And then who gives the oxygen to engineering? It is the incremental innovation. That is this little girl taught me, and I liked it. And then I asked Aurora Integrated, they're the first startup I mentored. They were my BTP student. And I was inspired by, I think, that time Professor Venkatesan was doing on more difficult problem of making autonomous helicopter. And I realized that these boys, they did very good. Not only these boys, Professor Amitabh Mukherjee, unfortunately he is no more, and Professor Rajat Munna, they helped in embedded coding, in writing the software. So these 5 boys, they made a good ecosystem. But my challenge to them was, if you can replace one of the Israeli product, then I am with you. The target was very simple. And they, one fine morning they came. I said, take this key, our so-called R&D lab, I used to tell, it's yours. And that is where the journey started. And I'll always mention this because at their age, when I was doing BTech, I was all the time thinking, can I get a job or not? Can I get a job or not? And these 4 boys, they were always talking about, do you want to open up a startup? In 2005, it was not so straightforward, right? And if you see here, I asked Nimish, what do you understand by you and me, if the title is this? And he says, you are the innovators, students, young scientists, imagining new possibilities. Me represents the ground reality, the soldier in the field, the mission that must succeed. The dialogue between you and me, between innovation and necessity is what builds nation's capability. This is the story of Indian drone journey, whether it was in IIT Kanpur, Venkatesan, or this Aurora. Parallelly, at the same time, Idea Forge was also working with a quadcopter. The best part I like for both the team is they started developing their own autopilot. With that time, open source was not there. That is exactly what I mentioned, Rajat Munna and Professor Amitabh Mukherjee. Yeah, next, please. So this title is given by Nimish. Said, from curiosity to capability, the vision that started it all. 2005, students at IIT Kanpur dreamt of building a UAV from scratch. The word scratch is important because we had a very good ecosystem in terms of aero modeling, right? There was an enthu in that. Then mentorship turned curiosity to capability and national necessity. Here I personally give thanks to Professor Mukherjee and Rajat Munna, especially for the autopilot part, right? I was as good as writing those transfer functions, not beyond that. Yes, next please. If you can run this video, this is my first time. Please understand, I was not a faculty candidate like Abhishek or Kamath and all. all learned people, right? I came from industry. I was with Pinaka, and suddenly the student expected I should know about aircraft. It's not easy for me. So first time after I taught design course, we designed this one configuration. And it did flew. Can you run the video if possible? Oh, this is the first one. That's all, only one. Doesn't matter. So this was weighing hardly 17 kg, right? And I wish the video had run. You could see I was standing at the back with being nervous, so I should not get exposed, right? And these boys, and that is the turning point. They came back, they said, we'll open up a startup, and that became the Aurora Integrated System with their own autopilot. And then those days, carbon composite manufacturing was not so easy, right? And they started doing it in, I think we have a mechanical engineering lab, and Professor Iyengar was there. So they guided, whatever way possible. Yeah, next please. Unfortunately, Professor Iyengar is also not there. And these young minds, they gave a title, From Lab to Battlefield. And it was consistent with my request, can you replace one Israeli bird, right? Autonomous bird. And you can see first one is basically, how do I do it? First one is the autopilot. Second one is the hand launch. That was, Army took that hand launch with a auto landing. And then they also developed 80 kg bird, 150 kilometer, those days, right? So imagine they worked on microHerd to extend the communication. And extended Kalman filter was not so available in the open source those days, right? Especially among the students, right? Because it was a fashion. How many state Kalman filter you are using, right? And that is how all the product, I think the third one went to Myanmar or somewhere, right? Next, please. So this is, I just refresh myself and pay gratitude to the student who taught me how to think about it. Now the question is from return on innovation to return on investment. There's one model. Tata invested some money, and Tata took the design. Even today, whatever loitering emission record orders Tata is getting, they use the same autopilot, but incremental innovation happened because they didn't make it VTOL, or what you call the conversion. Somebody made it conversion, somebody then, that's how it went. And in fact, the male UAV, the navigation loop is exactly same as it is being done, right? What is the difference? Difference is in the fail-safe and the flight management system. That is where so far, so much AI I was hearing. I think that taking a decision based on the situational awareness, AI perhaps will be able to help and take a correct decision rather than waiting for coded fail-safe. Next, please. And you see that the startup emerging from IIT Kanpur, and you are all aware now, View Dynamics, Endura AR, RF, so many, right? And they are handling, they are facing challenges. However, they have made an impact. I am saying, because I am not in an industry, okay? I see the response, what sort of a performance are happening, and I salute to these young boys and professors. They are really making an effort. So till this point, the debate was, if it is a fixed wing, so we'll say aerospace, we'll say a UAV is as good as its endurance and flight performance. If it is a drone, or so-called typical with quadcopter or hexacopter, well, it will be as good as the energy density of the battery. But then both were, shot. Suddenly came, a drone is as good as its payload. Drone is as good as its communication range, not the physical range. So indirectly, the opportunities are coming. Money is not there much. How can you do some delta incremental innovation and extend the communication range. Yeah, next please. Yes, the whole scenario changed. I was a member of Operation Sindoor analysis. I was coming back from there. And once I came back from there, now UAV is as good as electronic warfare or the jamming capabilities. So totally the scenario changed. And in fact, most of the surveillance UAV at 4 or 5 kilometers, they were drawn back, right? Because easily it was getting jammed. Harop was also getting jammed. Both sides it was getting jammed. So that again created an opportunity. Now the statement, if you see in the users, they'll say, what is the jamming capability? And second, more important thing came, standoff. If your range with the warhead is 50 kilometers or 100 kilometers, they say it's of no use for us. It should be at least 300 kilometers. And the speed. So that is another paradigm shift. Now you will see they're asking for launch from a ship. If launch from a ship means it has to be more than 500 kilometers because to protect the ship. And then launching from the ship itself is an art, is an attention to be drawn. So this, when this drone unfortunate conflict happened and the outcome, can you go to the next slide? If I just listed out the Operation Sindhu, of course, these transparencies are made by Nimish. I cannot make transparency, I gave him a hint, and that's all he made. All good is his, all bad is mine. If you see war situation context, contested air domain with layered air defense and electronic war activity, enemy use active jamming and spoofing, communication under denial, need for persistent ISR, rapid target handoff, and low latency strike decision, survivability and autonomy became key performance driver. And it got extended to aircraft also, right? Drones' role in operational impact, loitering ammunition, autonomous fixed wing UAS, and now this word Edge AI autopilot stacks enable local decision loop and fail-safe mission continuity. It is part of the word, and the computational power has increased. And counter EW techniques, frequency agile links, directional, low probabilistic intercept communication, and Kalman filter-based test estimation to resist spoof and jam. So this is, if you talk to military people, mostly they'll be talking about this in their own language, right? Next, please. And if you see world map of drone from recent conflicts, Ukraine, Israel, Syria, and Red Sea, it is giving an impression that drone is going to make a lot of difference. But my personal opinion, it will be too much to think that drone will replace aircraft, a drone will replace a missile, right? This is my personal opinion, can be contested offline. Okay, next please. This is not clear. If you see from, what do you call, Ukraine war, key drone deployment, swarm, FVB drones, and please understand, smaller startups are really working good in FPV. But then in a swarm structure, we need to look into it, how do you synergize that? And then similarly, different wars are there. You will see the almost, it is talking about automation, electronic warfare, fast decision making, and agile propulsion activity. Next, please. You see, This is conceptual, the next generation drone, high energy, aerodynamically elegant, stealth. So many parameters can be added. So people are anticipating, and networked. That's very, very important. The whole war is going net-centric. Next, please. Now, since morning, we are talking about artificial intelligence and autonomy. If you take me, I am talking from the user's point of view, as a user, me. The artificial intelligence and autonomy, the transformation in warfare, autonomous kill chain, adaptive swarm, predictive maintenance, AI-generated mission plans. What is the research implication? Build sovereign AI models for perception, navigation, targeting, establish ethical AI and human-on-loop doctrines. Second part comes communication and cyber resilience. This is new thing is coming today it may look futuristic, but 1 week back I was talking to one company. They have started working and mature to a level on cognitive radios, right, which is embedded with decision making, situational awareness, assessment, mesh relay swarm, quantum resistant encryption, GNSS deny ops. Whatever I am writing, most of them has come out after discussion with the people who are the users. Research implication: develop unjammable directional LPI links, national waveform standards, AI-assisted spectrum management. And then comes to the energy and propulsion. If we require the standoff range to be around 500 or 1 kilometer, let's say Harop type, extended Harop, NG, then what should be the propulsion thing? Are you going to use a Wankel engine? Are you going to use some other form of engine? So that's why you'll find, if you want to increase the endurance, what are the solutions? Are you planning to work on the hydrogen fuel cells? So these are some of the research implications we think may draw few attentions. Right, next please. Next. Just leave this one. This is repetition, this core research tracks, which is almost all we are talking about algorithm-based war. So what the common buzz is, the algorithm has entered the war. But then one need to also, today also I was hearing about AI, the algorithm needs data. Who captures the data? It's the sensor. We cannot think of algorithm or AI without giving due weightage to sensor development. So that is also one sort of a debate going on, and people are trying to see what is the solution. Let me tell you one thing. There's one discussion. If we go back to 1980, 82, 83, especially our IGMDB program, right? That time DRDL, it is told that it is a white elephant. And what was IGMDB? Integrated Guided Missile Development Program. What was the smart part of it? 5 missiles were selected based on what is available, what is to be extended, and what is common. For example, we have an engine, CUTSI ISRO, technology people are having. So do you think the time has come when we define integrated drone development program and select few drone, keeping in mind what is available, how much to be extended, and what are the cross-pollination? That sort of a, for example, you are making a test bench or test center. If you do not know what product you are making, it will be extremely difficult to know what we are going to test. Right? Next, please. This is again, if you see this 1, 2, 3, 4, 5, 6, 7, this was a half-hearted attempt to create a integrated missile technology development approach where a lot of weightage has gone into electronic warfare, processing, data collection, and application of AI, application of jamming, anti-jamming features. So in my opinion, the time has come when we need to have an integrated approach and focus on this and select few operational requirements. Next. Now I see in IIT Kanpur we have Center of Excellence and so many activities are going on. Why can't we integrate the Center of Excellence and create verticals, and they only work on that, right? Where the private party can join. So this is one of the approach. So the vision and purpose is written on the left, and core pillars is AI and autonomy, Edge AI, swarm logic. I must mention about Meher Baba, the way they are giving the challenges, which is also very, giving a lot of incentive to the young minds. Yeah, next. Next. If you see, the more important thing is stakeholder and role in ecosystem. Keeping in this mind, I am talking about integrated drone development ecosystem like IGMDB. The stakeholders will be defense and government agencies, define operational gaps, validate prototypes, and enable rapid induction. Academic and research institutions drive AI, autonomy, materials, and propulsion breakthroughs. Startup industry partnership with academia. Because today, if you see what from 2005 to 2025, we need not shout or loudly say. The examples are there how these people have took the challenge to the extent of logistics drone at a higher altitude, which many people could not do, and they have faced lots of problems. I think Endura Air, RAFE, something like that. But the challenges are there. Next, please. The future takes flight from IIT Kanpur to the nation. This is definitely from IIT Kanpur, and the legacy and what are the way things are going on. We do believe IIT Kanpur has an ecosystem, and that this may be the right place where the professors, faculty, students, and engineers work together. And the most important point is what to do, which one to start, which two if I start, there's the cross-pollination. That's sort of a mature decision make. Otherwise, we'll be scattered. We'll be doing this, we'll be doing that. That may not help in making a robust product. Next. I think that's all. And as I told in the beginning, this will be my perspective from user's point of view. Whatever I have interacted with them, especially after Operation Sindoor, I could see what they are looking for. One question was asked. We have so much of development in space program, development in missile program. Why such development is not there in drone program? I could not answer, because I'm not the right person to answer. But these questions are asked, but that means they want it. Okay? They believe in us, believe in our organization. Sorry, this is what I thought I will present only from the user's perspective, what is the requirement.